In all the preceding lectures, we considered an energy in which we have an elastic part of this type plus the sum of the cohesive energy due to jumps, which is concentrated on the jump points. Okay? If we consider a three-dimensional model, this energy should be a surface integral, okay? Because a singular point of the jumps becomes a surface. So the question is it this the only way of behaving? Why do we take the cohesive energy concentrated on the surface? Because one says, okay, because the fractures take place on surfaces. But there are different ways for producing a fracture, depending on the material. There on the board you see some different phenomena, which are just summarized. The first one is a Griffith brittle fracture, in which the non-elastic part is concentrated on the tip of the crack, and then you have the fracture of the body. In the other one, it is concentrated on a line in 2 dimensions, and this is the Barenbach model. But there are many cases in which the fracture has a process zone near the tip of the crack, which is of the same dimension as the body. Okay, so looks like one should use different energies for these different phenomena. So the idea which came out is why we don't think that the cohesive energy has a volume density, and when the loading proceeds, maybe this cohesive energy concentrates spontaneously just by energy minimization on a singular surface. And this is the origin of the model I am going to present here, in which I take a cohesive energy which is a volume. Not this way. I will write better. I will write the correct formula in a minute. So to take a cohesive energy which has a volume density, and then to say the concentration of the inelastic deformation on a singular surface is just a phenomenon of localization which could be governed by the equation of the problem, and depending on, of course, on the shape of theta again. So the idea is the following one. We have the axial deformation. We suppose that this axial deformation be the sum of 2 deformations, one elastic and one inelastic. Yes, now I am in 1 dimension. So this is elastic, this is inelastic, and they are not the gradient of anything. Okay, and this decomposition is usually in plasticity. Okay, plasticity, we have elastic part and plastic part. I don't wish to call it plastic part because I don't wish to make a theory of plasticity. Okay, then a second hypothesis that we do is that the total energy is the sum of 2 parts, one depending on the elastic deformation and one depending on the inelastic deformation. And both have a volume density. Okay. This is what I was trying to write here, but it was missing the decomposition of the strain. So we have an elastic part and an inelastic part of the energy. As I said before, I don't wish to call it plasticity, but what comes out, if we now make minimization of the energy, we find exactly plasticity. I mean, the classical plasticity by Hill, by Prager, had some phenomenological assumptions, okay? For instance, elastic unloading and so on. And by minimizing this functional, we will find exactly these assumptions, not anymore as assumptions, but as consequences of the minimization. And this is a very surprising result for me, and we will see why. We add something. I mean, we add that this part is completely dissipative, just because we saw yesterday that if we wish to have elastic unloading, we must assume that theta is dissipative. And this is again the same equations as yesterday, theta prime, gamma dot, greater or equal than 0. And because we are still assuming theta prime positive, we have the same dissipation inequality as yesterday. And and then we have boundary conditions, which says that the integral of u prime must be equal to beta L. Okay, so we write that beta L. Beta L is the integral of epsilon plus gamma. And I can divide by L, so I can write that beta is equal to the average of epsilon, okay, 1 over L by the integral, which I call epsilon, plus the average of gamma over 0L. Okay, so this is my boundary condition. So now we have to minimize this energy subject to this dissipation inequality and to this boundary condition. And then we start turning the machine. I mean the machine is always the same, but the results are different, and we have to discuss them. So we start with equilibrium configurations. Equilibrium configurations are those for which the first variation is greater or equal than 0. So we write, so this E and we write the first variation by taking perturbation delta epsilon, delta gamma. Of course, delta epsilon average plus delta gamma average must be equal to 0 because I take a perturbation which doesn't change the total length of the bar. Okay? And again, delta gamma has to be greater, delta gamma of x has to be greater or equal than 0 because I take only the perturbation which lead to accessible configurations, as we did before. So let's write the first variation. Which is w prime of epsilon multiplied by d epsilon plus theta prime multiplied by delta gamma. And we do operations that we already did for the simpler model. That is, now, first of all, we take a perturbation with delta gamma equal to 0. That is a purely elastic perturbation. Okay? And from this, using the same lemma, calculus of variation we used before, we again find that W prime of epsilon is a constant, and this constant is the axial force. So W prime of epsilon is equal to sigma for all x. And again, because W prime is strictly monotonic, we find that epsilon of x is a constant which is equal to its average. And I call it simply epsilon from now on. So we have this first result, which is obtained, as I said, by taking purely elastic perturbations. So, because this is constant, we take it out of the integral. So we have W prime of epsilon, or sigma, as you prefer, multiplied the integral of delta epsilon. But the integral of delta epsilon is equal to minus the integral of delta gamma. So I write minus integral of delta gamma. And then I can collect the delta gamma, and what I get is let me just write it, plus integral theta prime okay. Now I can put this W prime again inside the integral, okay? And I can collect the delta gamma. So what I get is integral from 0 to L, theta prime minus W prime or sigma, as we like, delta gamma of x greater or equal than 0. So this is a condition of equilibrium, a second condition of equilibrium. So because delta gamma is arbitrarily positive, this parenthesis has to be greater or equal than 0. And this is the second condition for equilibrium, theta prime of gamma dx greater or equal than sigma. So we have two consequences of equilibrium. One is this, and one is this. Of course, I have less or equal because I have the dissipation, just as yesterday. So this second condition tells us that the axial force has an upper bound. But this upper bound depends on the punctual value of gamma. And this, if we make the comparison with plasticity, this is a yield condition, which says that the force cannot go beyond a certain limit, a certain elastic limit, as it is called. So with equilibrium, we have found a yield condition automatically. And again, it is possible to prove that this. There is nothing that this is trivial. If these conditions are satisfied, then the first variation is greater or equal than 0, and then I have an equilibrium configuration. So it is on the two ways. This is so. These two conditions are the definition of an equilibrium configuration. Okay. And let's look about the stability of this of the equilibrium configuration. For the stability, we look at the second variation. So the second variation is second variation here I simply write delta gamma because we have seen that delta epsilon is constant and equal to minus the integral of delta gamma. So I forget about that. So we have the integral w double prime so in place of delta epsilon I can write minus delta gamma square. Delta gamma, this is a constant, so it is equal to minus delta gamma square is delta gamma square, plus theta double prime of gamma of x delta gamma square of x. And the necessary condition for stability is that this second variation be greater or equal than 0. Okay, so we have here a strange fact. Here we have the average and here we have the function. Okay, we are free to take any non-negative perturbation. So let's assume if theta double prime is positive, it is clear that the sum is positive, so there is no problem. Assume that theta double prime is negative at a certain segment of the bar. Okay, so we have the bar 0L, and we suppose that here theta double prime is negative. Okay, so I take a perturbation of this type. Don't worry about the regularity. This is just for simplicity. I can take it as smooth as I wish. This is my delta gamma. This is epsilon. Okay, and this is 1, say. So that the area is epsilon. So gamma bar, which is the integral of the average over 0L, is epsilon over L. So for this perturbation, here I have the integral, let me start from here. This is constant, okay, W of epsilon. The integral of delta gamma square, this is delta gamma, is epsilon square over L square. Multiplied by epsilon, which is, okay, multiplied by L, because this is all over L. Plus theta double prime multiplied by delta gamma, which is 1, multiplied by epsilon, which is the length. So it is not necessarily constant. Integral of delta gamma multiplied by 1. Integral over something whose length is epsilon. Okay? So this is like epsilon, this is like epsilon square. This term is dominating, this term is negative, so the second variation is negative. Okay? So with just one moment. This means that if I concentrate the perturbation on the region in which theta double prime is negative, I get a negative second variation, and therefore the configuration is unstable. Yes, please. Oh, okay. This is epsilon, which is the length. Okay, I used it twice as the same symbol. I am sorry for that. This is the epsilon. Let me pull it a hat. Okay, this is a hat epsilon. I'm sorry for that. Okay. So we have this, which, as we shall see, is a weak point of this model, that this model does not accept a theta double prime negative. Okay, theta double. That is, theta double prime has to be convex. So, as a condition of stability, we have theta double prime of gamma of x greater or equal than 0. You just must be a little bit patient, because I will come to the point. Okay, you are completely right, of course, but I will come to the point. No, you are making comments, you are welcome. But I just say I will answer. But I have some good reason for saying that, and you will see. Okay. So, of course, these conditions are not sufficient to determine the evolution. So, as we said yesterday, in the dissipative case, we prescribe a process of beta, and we wish to determine we wish to determine the process of the configurations. Okay, but before writing what are configurations, I make a small change here, which I already did yesterday in the case of a punctual cohesive energy. So the observation is always the same. The energy is a function of epsilon and gamma, but epsilon and gamma are related with beta with by this relation. And of course, because beta is known, it is convenient to eliminate epsilon and to express everything as a function of beta and gamma. So we eliminate the epsilon. So we write an energy which I call energy of equilibrium, because this is true only for equilibrium configurations, as a function of beta and gamma, which is simply the equilibrium, so I take it out of the integral. In place of epsilon, I write beta minus gamma bar. Plus the integral and it is convenient to make reference to this energy. So here, for me now, a configuration is just a pair beta gamma instead of epsilon gamma, okay? And so I wish to find the evolution beta of t, gamma of t. Of course, beta of t is known, is given, so what I need essentially is to find the gamma, okay? And I recall what we said yesterday. We have some initial condition at t equal to 0, and then every configuration has to be a weak local minimizer, and every configuration must be accessible from the preceding ones. Same requirements as yesterday. So we consider an evolution problem for this functional. And again, we wish to determine what happens at time t plus tau, knowing everything at time t. So we take an expansion. So for this energy, we say that this energy at t plus tau. So I should write beta of t plus tau, gamma of t plus tau, but to be shorter, I just write it this way, is equal to the energy at time t plus tau, plus t times a first order term plus 1/2 tau square, a second order term, plus higher order terms in tau. And we wish to minimize this sum. This is known, so it is not a matter of minimization. And we start with minimizing this. So the time derivative of the energy with respect to t. Okay, so let me write this here. So this is simply integral 0 over L W prime of beta minus gamma beta dot minus gamma dot bar plus theta prime of gamma dot. So this is a constant. We take it out of the integral, and this is sigma, essentially. This is sigma. So we have sigma L beta dot. This is the first term. Then we have plus, I write first that term there, theta prime of gamma of x, minus, this is a constant multiplied by the integral of gamma. L gamma dot, the integral of gamma dot, but the integral of gamma dot is the integral of gamma, okay? So we have minus sigma, gamma dot is out, okay? Gamma dot of x dx, okay? Clear? Okay, so we have a constant here, something which is given, plus this product. In this product, this is greater or equal than 0 by equilibrium, and this is greater or equal than 0 by the dissipation inequality. So the whole term is greater or equal than 0. Then it is very easy to minimize this term because the minimum is 0. Okay, so we write here that the fact that this product has to be 0. Okay, we can add to this condition some conditions that we already have, that is dissipation inequality and the equilibrium condition. And you see that this set of conditions is a set of Kuhn-Tucker conditions, which is formally correct because we are minimizing a functional in the presence of inequality. So in place of the Euler equation, we should have something like that. Which is, as I said, we don't get much information because we say that the first derivative is a constant plus something which is 0. So this is a constant exactly like yesterday. So this doesn't give any information. We have to minimize this. But we have an important information here. And this is given by the complementarity condition of the Kontaker set. Because this tells us that to have gamma, if we are at an interior point of the elastic domain, that is, if this inequality is strict, this inequality is strict, then gamma dot has to be 0. That is to say, I can, the inelastic deformation can increase only at points which are at the border of the elastic domain. Okay? Which is a usual assumption of plasticity. And again, we find it as a consequence of minimization. So when I go to minimize the second order term, I must keep this information. So the gamma dot is not arbitrary over the whole bar 0L, but only at those points at which this inequality is verified as an equality. Okay? So for the second order term, I don't write an integral extended to 0L, but only an integral extended to the elastic region. And the elastic region, which I denoted with a script E like this, of a configuration beta gamma, is the set of all points of the bar, such that this inequality is verified as an equality. Sigma, which means W prime of beta minus integral of gamma equal to theta prime of gamma of x. Okay. Okay. So in the next minimization, the integral is not anymore over the whole bar, but over this set. Over the complementary of this set, because on this set gamma dot is 0. Okay? So I call capital I of beta gamma the complementary set. Just because you verify the yield condition with inequality, you are inside the elastic. Okay, I am sorry. I am sorry. Yeah? This is a capital E. Yes, script E, like that. Okay, so this is. Oh. So the integral will be made on this region. We assume that it is an interval, but of course an analyst should protest about that. Yeah, yeah, but if it is a set of measures 0, the integral has no is 0. So, okay. So I wish to keep this because this is a definition. Okay. So the second minimization is about the integral over this I of beta gamma, I don't write the beta gamma, of W prime of beta minus gamma beta dot minus gamma bar dot square plus theta double prime of gamma of x gamma dot square of x. So we have to minimize this. And writing I here, I already took into account this condition, okay? And then I still have this condition here. Okay, so the minimization here is not as easy as for the first order term. We have to do exactly a minimum. So what we consider? We consider the first variation of this functional. Okay? So we evaluate this functional at gamma plus delta gamma. But we have to be careful about that, because we are used to minimize in a set of functions which leave the length of the bar unchanged. Here, the length of the bar is not unchanged because we have a beta dot. Okay? So we are minimizing over a set of functions for which the change of length is given but is not zero. Okay? So assume that this is a set of all equilibrium configurations for beta. And this is a set of all equilibrium configurations for beta plus beta dot. We are here, and we wish to minimize here. Okay? So the minimum will be some gamma, which we don't know. Will be our candidate gamma of t plus tau. And this is gamma plus delta gamma. And this is a perturbation delta gamma. Okay? So usually we ask delta gamma to be 0, but not here, greater or equal than 0, but not here, because here the accessibility is from here and not from here. So now we have to require that gamma plus delta gamma be greater or equal than 0, and not delta gamma alone. Okay? Because this must be the accessibility path, and we minimize among all configurations here which are accessible from here. So this is the two condition, and we have to forget about the other one. And this is fundamental to get what we wish. So now let's do that. So let me write it here. So I have that EW dot is equal to the integral of the inelastic zone of W double prime of beta minus gamma multiplied, here I have a square, then I have first a beta dot square plus minus twice beta dot gamma dot plus gamma dot square plus theta double prime of gamma dot square dx. I have this. So we can forget about this term which is given and doesn't affect the minimization. So apart, this is a constant. I write constant here just to remember it. Then we let's write the first variation. Okay. At gamma with a perturbation delta gamma. So in the first variation, this term is the same, so gives a contribution 0. Here we have a factor 2, which multiplies W double prime beta minus gamma multiplied by beta dot and multiplied by delta gamma, but I will put delta gamma at the end. Plus, here I have twice gamma dot delta gamma dot plus, and the 2 is already here, plus, and this is multiplied by W, okay, so it is this way. And this was a minus. Okay. Plus theta double prime of gamma of x twice gamma dot of x, and here at the end I put delta gamma dot of x for everything. Okay. Here I have a gamma dot should be delta gamma dot bar, but because the coefficient is constant, I can eliminate the bar. Okay. So this is the first variation, and we can rewrite it in the following way. I forget about the factor 2, and I write here. I write, you see, sigma is equal to W prime of epsilon. Sigma dot is equal to W double prime of epsilon, epsilon dot. And so this part here is exactly minus sigma dot. So let me write first this one. Theta double prime of gamma of x, gamma dot of x, minus sigma dot de gamma dot of x greater or equal dx greater or equal than 0. Okay. And of course, I can localize this condition. Okay, and to write simply that this term has to be greater or equal than 0 for every x in the region I. Because I can localize, I can take perturbations which are 0 almost everywhere in the interval. So, we see here, we have to be careful now because we have this condition, okay? So, we are in the region I, in which gamma dot is allowed to be positive, but can also be 0. Okay? So we have two possibilities. Gamma dot can be 0 or different from 0. So if gamma dot is 0, delta gamma dot has to be greater or equal than 0. Arbitrary, so this parenthesis had to be greater or equal than 0. Okay, so this is the first possibility. If gamma dot, I mean gamma dot at x, I didn't write, but I am I am considering a single point x. If gamma dot is positive, then this parenthesis has to be equal to 0. Because the product is 0. One moment, it is not so direct. If gamma dot is delta gamma dot has no sign, can be positive or negative. Okay, so for that reason, this maybe have any sign. This has to be 0. Okay. So we see that either gamma dot or the parenthesis is 0. One or the two has to be 0. So we have a second set of Kuhn-Tucker conditions, which I write here. We have the first inequality is always a dissipation inequality. The second inequality is just that the parenthesis has to be greater or equal than 0. I don't write the x. This is for a single x. And then I have the complementarity condition that the product of the two has to be 0. Okay. So this is a second set of complementarity condition. What does it say? The first one says that if gamma dot is positive, we have the permanence on the boundary of the plastic domain, because this is evolution is exactly what is needed to remain on the boundary. Okay. No, I'm sorry. We have inequality. This would be true with equality. Inequality means that we cannot go out. Okay, the sigma dot either stays on the boundary or comes in. And this condition says that when it comes in, that means when this is greater than 0, gamma dot has to be 0. So this is again elastic unloading. So here we have, this is called consistency condition by Prager, by Hill, and so on. So here again, we have some assumptions which belong to the history of classical plasticity, but here they are not assumptions, so they are just consequences of a careful minimization. And this constraint is essential, as you said, as you saw. Huh? So we have all this information here and here. And now we can see whether this information is sufficient to determine the evolution. Yeah. Yeah. Go further. I don't think so, but first of all, it is difficult to think to something that has this kind of regularity. Here, for instance, we have just gamma dot, theta double prime. We can conceive that they are continuous. If they are not continuous, we have some trouble. The higher you go with the derivatives, the more trouble you have, so it is not trivial. What I am going to prove now is that this piece of information is sufficient to determine, in this case, the evolution. You say maybe there could be some contradiction. This is your point. Yeah. If you have the regularity, which is not peaceful, I mean. I agree, yeah. Yeah. But Yeah, but this is a criticism that you could make to calculus of variations in general, because even there you have conditions on the second derivative of the second variation, and you could object that you can take any variation, and okay, so I leave open this point, because turn it to Andrea Braides if he's here, or any other specialist in calculus of variation. Okay, so I was saying, let's see whether or not this is sufficient to determine the evolution. I speak. I didn't understand it. This condition, this one, the complementarity condition, this one, gamma point bigger than 0, this one. If gamma point is greater than 0, then the sign of delta gamma point is free. If it is free, the sign of gamma point, to verify this inequality, this has to be 0. And it is simply equal to 0. So the product of either you have this or you have this. So the product is always 0. This here I have gamma point, and here I have this parenthesis. And I proved that either gamma point is 0 or the parenthesis is 0. So the product is always 0. This one? No, this is, yes, it should be, exactly, it should be gamma point equal to 0. I didn't write it, but in principle, yes. No, he says if gamma point is 0, when this is greater than 0, this is 0. Correct, but for the moment we are not interested in that. Okay. So what we do now, we consider an evolution starting from the natural configuration. Natural configuration means beta equal to 0 and gamma equal to 0. At this configuration, sigma is equal to 0, because beta and gamma are equal to 0, and theta prime is theta prime of 0. Okay? So we have, on the two sides of that inequality, we have theta prime of 0 and 0. And theta prime of 0 by assumption is positive. Okay? So in this, at the starting point of the evolution, this product here, this product here is, this product here is positive. So gamma dot has to be 0. So that means that when we start from the natural configuration, just because of that inequality, we have no inelastic deformation. The response initially is elastic. Okay? And if we continue, here, in place of theta prime, here we still have theta prime of 0, because there is no inelastic deformation, and here we have sigma. Where gamma dot is 0. Okay? And beta is increasing, and W prime of beta, yes. And there come a moment in which beta reaches the value for which this inequality becomes an equality. And this value of beta, I call it beta sub c, and we find that beta sub c is equal, same expression as yesterday, W prime to the minus 1 of theta prime of 0. Okay? So up to that value of beta, we have an elastic response. Okay? So what happens at this value? At this value, we have equality. That means the whole bar, which before was in the elastic region, is now in the inelastic region, because the inequality is satisfied for the whole bar. Okay? So this set of conditions applies to the whole bar. Okay? So let's examine the homogeneous solutions. I mean, let's assume, this is not the only possibility, but let's assume that the gamma dot is positive at every point of the bar. So, from here, now we have that gamma dot. We are in the limited situation in which this is equality. Gamma dot is equal to sigma dot divided by theta double prime of 0, because at this instant gamma is still 0. Okay? So we have this gamma dot. And this gamma dot, either it is 0, and this is a trivial case, or it is positive. So now we consider the case in which theta double prime is strictly greater than 0. Otherwise, we cannot put it on the denominator. Okay? So we have this gamma dot. And this is, of course, this is W prime of beta C multiplied by W prime of beta C, sorry, this is sigma dot W double prime of beta C, beta dot minus gamma dot bar, divided by theta double prime of 0. And now if we take the integral over 0L here, we get L gamma bar dot. Okay? And this is a constant, so we have L multiplied this constant. The L you can forget about. So we can determine gamma dot from here. We have theta double 0 gamma dot plus W double prime of beta C and of 0 plus double prime of beta C gamma over theta double prime of 0 gamma dot equal to W double prime of beta C over theta double prime of 0 beta dot, which means we can't forget about that, which means that gamma dot average, which is equal to gamma dot because we saw that the formation is homogeneous, is equal to this divided by this. W multiplied by beta dot. Okay. And then eventually we can calculate sigma dot. So we have a double prime of beta c multiplied this. So if I reduce to the same denominator, I have w minus plus theta double prime minus w double prime. So this is theta double prime divided by this. Multiplied by beta prime, beta dot. Okay, so we have got everything because we have the closed expression of the gamma dot, and this gives us the slope sigma dot over beta dot, the slope of the response curve. And you see that the slope is positive, because everything here is positive, and is less than the slope w of double prime of beta c of the elastic response. So we have something like that. This is the elastic part, which ends at beta sub c. This is a sigma, and then we have a lower slope. Okay. In the case theta double prime equal to 0, I don't make the computation, but here we simply get sigma dot equal to 0. So we have the perfect plasticity. And for theta double prime less than 0, we have instability because we saw that it is unstable. And if we make the computation, we have something that goes to minus infinity, that is the brittle fracture. Okay? So we have a complete picture of what happens starting from the natural state. You see here on the left, this theta on the axis is wrong, it should be sigma. If we have an energy, like in the graph of the right, that is first convex, then concave, gamma L is the inflection point, then up to beta c on the left graph, we have the elastic response. Then from h to k, we have the inelastic response, and the slope, as we see, depends upon the value of theta. Because the flow rule is something related to higher dimension. Yeah, in one dimension it is trivial. Yeah, but it is trivial because flow rule gives you the direction of the normal. Here you have the segment direction of the normal. It's just one possible. So, okay. So, if we repeat the calculation, now this formula holds at the point h, that is at the beginning of the inelastic deformation. But since I have a constant gamma dot, I can go further, and I have the same equations, with the only difference that instead of having 0 here, I have the gamma. So this equation becomes sensitive to the shape of the function theta double prime. And this is why you see from h to k a variable slope. Okay? Point k is the inflection point where gamma is equal to gamma r. At this point, the curve becomes horizontal, but just after, you have theta double prime negative, so you have the rupture. This is the answer of this model. Okay, so this answer gives something, this is certain, but has a weak point. The weak point is that you don't see any response with a negative slope, which is called, this is called work hardening. You don't see any strain softening, which is a response with a negative slope, which is very common in plasticity, and from the viewpoint of the theory is the most delicate point. So this model is not strong enough to take strain softening. Gives this very rough response that as far as theta double prime is positive, you have either positive of zero slope and then immediately go to minus infinity, because you have this possibility of concentrating the deformation in a very narrow segment, and this makes the energy to go to minus infinity. So there is something wrong intrinsically in this model. Okay, something inadequate to describe the physics. So what could we do? Yeah. Sorry? In higher dimension, I believe yes, but I didn't check. Probably yes. Because the point is that you cannot stop a unlimited concentration of the formations, and this remains for higher dimension. So what we need is some mechanism which doesn't allow the inelastic deformation to concentrate too much. And this a remedy to this is something that listening to the lectures of Enrico is completely trivial, but so what we do simply is to add a Cahn-Hilliard term, that is a term which penalizes the first derivative. Okay. And this will be the object of the lecture of tomorrow. That is, we said that the reason for this dramatic change when theta double prime becomes negative even at a small interval stays in the fact that I can concentrate the deformation there. So I can take a gamma dot made this way with this epsilon as small as I like. Okay? But now, if I take an epsilon of this way, its derivative, its partial derivative is high. So I have a competition between these terms here, which tend the energy to go to minus infinity, and this term, which goes to plus infinity. Okay, and of course, the good compromise to get the minimum strongly depends on that alpha, on that numerical parameter alpha. So, in principle, we keep this alpha small because we wish to make what mathematicians call a singular perturbation. That is, we don't wish to change completely the physics of the problem, but just to add a small term which eliminates the most undesired behavior of our simple model. If alpha is very large, the response could be completely different to that one. Yeah, but we would. Yeah, but we would like to know more about strain softening, because this is a very crucial point. To just, you know, when you make. Okay, yeah, perfect. Yes. You change completely the response. What I'm saying, for instance, if you make a test on a bar, a tensile test, you get a diagram of this type, roughly. You get a maximum, then with our model you arrive here and they go down. So you lose everything of this part of the diagram, which is important because this part of the diagram doesn't add anything to the strength of the bar, because the strength is given by the maximum sigma, but adds a lot to the ductility. That means to the capacity of deforming before rupture. Okay? Here is a prediction that at this point the bar breaks immediately, and this is not true. The bar can still be elongated. This is sigma and this is beta. Sometimes for a lot, before having the final rupture. So in the analysis we will make tomorrow, we will be interested in studying this part of the curve, which cannot be done with our model as it is. Okay? So the crucial thing was to take the cohesive energy as a bulk energy. And as I said, on the energy minimization made carefully. So we will be able to take this effect. And this effect is extremely well known, because you know that when you pull a bar, before rupture, there is a phenomenon called necking. It is a striction of the central part of the bar. This striction corresponds to an elongation in the axial direction, just by Poisson effect. That means that when you have the formation of necking, the deformation is localized in this zone. So the gamma has a diagram of this type, say. Here it has some value, here has a peak, and so on. And we will see that with this additional Carnelian term, we can take this effect. A last comment, as I told you before at the beginning, this plasticity-like response comes from the two initial assumptions. First one is the composition of the deformation into elastic and inelastic part, and then the composition of the energy in the same way. This is not the only possibility that we have. We have many possibilities. For instance, one possibility is the one which is being explored by Jacques Marigo, and this possibility is simply to take an energy which is a function of displacement and of a damage parameter, which is a scalar parameter between 0 and 1. And to take an energy in which there is a couplet dependence upon U prime and alpha with the laws of damage, okay, which I don't specify now. With this approach of Jean-Jacques has the same characteristic of having this alpha as a bulk, as a volume parameter, and not as a singular surface. And even in his study, this parameter can localize over singular surfaces and so on by minimizing the energy. What he does is very similar to what I am doing. And I think he will speak of that on Saturday. No, today is on fatigue. It's something different. Yeah. And so, as I said, this method, say, of study of energy minimization is not limited to what I am doing now. I just made one of the possible choices, but the method is much more rich. So we can figure out not only damage, but we can figure out any other type of response. Okay, I guess I can stop here.
Okay, I will try to speak in English and translate something in Italian. Okay, this conference and the symposium after the conference and the prize are all financially supported nearly completely by the Fondazione Tullio Levi Civita, the president of which is Dr. Mauro Carturan, and by the province of Latina, the president of which is the president Cusani. The idea which was under these initiatives is always the same. The local administrations feel that higher education needs to be rooted in this province. So they want to attract young generations of this province to start research. And the only way is to have serious research taught and developed here. So in Cisterna di Latina we have some activities in the Palazzo Caetani, which is the feudal castle of Caetani family, which is now owned by the city of Cisterna. And here in Sperlonga you see this beautiful church, and all the city, how beautifully has been restored, by the way, by the mayor, Cusani, who was the mayor here before becoming the president. So it is better that we don't lose too much time. I will simply tell that Professor Carlen from Rutgers University is an expert in statistical mechanics. We wrote the Laudatio, and it is available in your website, I mean of the province, and in the website of the Fondazione. And Professor Marigo, I worked all my life on the books and ideas of a famous French mathematician, Cauchy. So I was surprised in discovering that he is the successor on the chair of Cauchy. So not only he wrote very good papers, but he also has the responsibility of continuing a very ancient activity, high research activity. I don't want to say that in the United States they are not doing very well, by the way, but you know, we are old-fashioned. Okay. So I think that you can talk in Italian as you prefer. I will try to translate later. Anyway, everything is recorded, and all lectures will be available online. So there is an evident proof that we try to leave a footprint. Okay. So.
I don't speak in English, io posso solo dire in inglese welcome in Sperlonga, welcome in provincia di Latina, welcome in Fondazione Tullio Levi Civita. È la scuola estiva che si ripete, ci fa piacere che ogni anno si arricchisce di professori illustri. Per noi è un motivo importante anche di promozione per le nostre attività. Per quanto mi riguarda, io guardo con grande attenzione agli studenti del nostro territorio, naturalmente anche a coloro che si incontrano qui provenendo dalle varie parti d'Italia, e a livello internazionale per noi è sempre un piacere, però le attività di un ente locale sono quelle di cercare anche di integrare dal punto di vista culturale le attività dei giovani del nostro territorio. Insieme al Presidente della provincia abbiamo iniziato a lavorare sulla scuola di formazione per gli studenti che guardano l'università, abbiamo avuto la fortuna di mettere a bando un po' di borse di studio per l'eccellenza, stiamo tentando di fare anche studi universitari e favoriamo anche la ricerca. La ricerca però non compete all'ente locale, quindi noi facciamo la capriole per stare dentro in queste cose. non aggiungo altro se non ringraziare il mio presidente Cusani per aver intuito quello che stiamo facendo e per scommettere su questa cosa. Purtroppo sulla cultura e sulla scuola è sempre difficile lavorare, perché il mondo della politica guarda più agli interessi che non alla formazione, figuriamoci poi alla ricerca. Per cui il ringraziamento speciale gli faccio oggi, sperando che l'investimento che lui sta facendo su questa cosa possa dare i frutti. Siamo onorati di avere questi illustri ospiti e tutti voi qui a Sperlonga e sul nostro territorio e nei nostri ambienti di ricerca. Quindi un ringraziamento speciale, complimenti per i premi che vengono assegnati, nella speranza che vengano utilizzati per la ricerca, per le vostre attività che già avete svolto, quindi di merito, ciò che state facendo ogni giorno, ricordandovi che c'è un lembo di terra, quella nostra, che oltre che essere fucina culturale è anche ospitale, e qui stiamo in uno dei più bei posti d'Italia e questo è anche motivo di orgoglio. Grazie.
Our president wants always to underline that research is not directly competence of a local administration. However, he underlines that he succeeded in financing research activities. I already told you in a sense already. The aim of the local administration is to let to everybody know how beautiful is Sperlonga and how beautiful is the province of Latina, and they want to let to know to young generations of this province that higher education is important. So attracting scientists from all over the world, their aim is to try to produce scientists or very specialized intellectuals here. Okay, so this is the importance. Okay, so
io voglio aggiungere alle cose dette dal professor dell'Isola e dal presidente della fondazione soltanto il fatto che la nostra presenza, anche del rappresentante del comune, manifesta l'impegno concreto, non soltanto quello nelle risorse, nell'essere vicino a questa organizzazione che abbiamo messo in piedi, come diceva Mauro Carturan, un po' contro tutte le volontà ordinarie, quindi cerchiamo di portarla avanti puntando a io li definisco rivoluzionari della cultura nelle università, tipo il professor dell'Isola, e quindi lo facciamo perché ci crediamo, ma la nostra presenza è conferma dell'impegno anche in prospettiva futura, anzi vorremmo che presto questa diventi una scuola titolata per essere una scuola riconosciuta anche a livello nazionale. Noi siamo assolutamente convinti che bisogna investire sulla scuola, sull'istruzione, sull'educazione, su tutto ciò che c'è dentro la mente delle persone, sulle potenzialità che gli individui possono esprimere attraverso il mettergli a disposizione le conoscenze e i saperi. Ma nell'ambito di questa affermazione generica bisogna puntare sulle eccellenze, sui migliori, perché quelli fanno forte una comunità globale. Quelli sono i soggetti che consentono anche di rispondere concretamente al preambolo dell'UNESCO, che dice le guerre iniziano nelle menti delle persone ed è sulle menti delle persone che noi dobbiamo costruire la pace. Però abbiamo bisogno dei migliori. E tra i migliori, nelle varie culture, quella scientifica in Italia soprattutto è diventata un po', nonostante noi abbiamo iscritto la tradizione dei matematici, del mondo scientifico, i più bei personaggi, i più grandi personaggi, è un po' in difficoltà. Noi abbiamo pensato di prendere al volo l'idea, come dicevo, di un rivoluzionario della cultura da questo punto di vista, che è il professor dell'Isola, e sostenerlo senza infingimenti, senza se e senza ma. E lo facciamo, ha ben detto il presidente della fondazione, perché ci crediamo, perché siamo convinti e coscienti che facciamo un buon lavoro per la comunità anche nazionale, non soltanto per quella piccola di 600.000 abitanti che noi rappresentiamo, perché è nostro dovere farlo, non lo facciamo perché tra l'altro su questi investimenti non si ha consenso, su questi investimenti non c'è un interesse speculare o strumentale, lo facciamo perché ci crediamo, perché se lo facciamo in tanti probabilmente, ecco, alimentiamo quella speranza di avere un mondo migliore che guarda alle persone migliori, a quelle che hanno, diciamo, per fortuna rispetto ad altri, delle grandi intelligenze che devono essere però coltivate, che devono essere sostenute, che devono essere alimentate. Ecco, il nostro impegno è racchiuso in queste formule, in queste espressioni, per cui noi ci tenevamo, io ci tenevo in particolare anche con Mauro Carturan, tra l'altro, che non a caso è il presidente di questa fondazione, perché per fare il presidente di una fondazione di questo tipo bisogna avere una sensibilità molto spinta e bisogna crederci fino in fondo, bisogna sapere che cos'è, di che cosa si tratta, che cosa fa. Non ci sono volontari, non ci sono file, non abbiamo elenchi che vogliono fare presente la fondazione, quindi questo dà anche la misura di come tutto sommato, ecco, scegliere la persona alla guida di una fondazione di questo tipo non è scelta casuale, è scelta oculata. Per cui ecco, noi ci tenevamo anche nelle nostre complicate giornate come le vostre, magari le vostre si concentrano più su un filone, le nostre sono complicatissime, molto più complicate perché molto più variegate, ci tenevamo, ecco, a venire qui non soltanto, come dicevo in premessa, a testimoniare il nostro impegno per il futuro, ma anche a stringere la mano ai due personaggi che sono stati selezionati e messi a disposizione di questa scuola estiva. Grazie.
It is embarrassing because the president was talking too much about me, so I will simply tell you that he believes I'm revolutionary. Maybe I'm only crazy. However, it is important to hear from an Italian politician that research is important. I am very happy and I will fight as I can for sustaining this kind of politicians. So thanks you for being here. Okay. We have, for the moment, we have 3 books each about the city, but of course the prize will be sent in a more discreet way to both of you, okay? So these are describing the city and the story of the city. Grazie. Sì. Grazie. Grazie. Arrivederci. Ciao. Okay, so please start your presentation. You have an hour, more or less. Okay, I was wrong. Professor Presutti will talk tomorrow. Please, we should be here back at 4 o'clock. There will be 2 lectures by Professor Marigo, and we will end earlier than forecast in the program. Okay? Thanks. 4 o'clock, okay?
Okay, so, well, thank you very much. I'm very honored to be here, and this is my first visit to Sperlunga. It's a beautiful place, a beautiful conference, and I'd like to thank the organizers very much for the opportunity to speak here. The talk I'm going to present is aimed at graduate students as requested, and I'm going to try to present a point of view of a kind of class of calculus of variation problems that is slightly different from some of the ones I've been hearing about here. It is more focused on finding near minimizers than minimizers, and I'll try to explain why this is physically important and therefore why some of the techniques are somewhat different. In particular, Euler-Lagrange equations will play essentially no role in this investigation, but rather a certain kind of stability for sharp inequalities plays a prominent role. Okay? Now, the talks I'm giving here, the slides have been cut down from a longer course I gave at the other end of the summer. There was a summer school in Ischia, and if you want to see more and more detail, there's a fuller version with a series of 6. Is this better? Okay. Okay. Okay, that's right. Okay, is that working well? Good. Okay, so you can find on the web, if you search on my name and Ischia, you can find a full long version of this, okay? But let me begin by telling you, well, let me begin. The results I'm going to talk about here are drawn from work with various co-authors. 2 of them are right here, Lello Esposito and Rosanna Mara, also Maria Carvalho, Joel Leibowitz, and more recently Francesco Maggi. So there's a large Italian contingent in this, and I'd like to begin by thanking these co-authors and talking first about what I mean by a type of stability inequality. So here's a very simple example, and it's something that will be familiar. It's an idea that's come up in several of the lectures I've seen before. If you have a convex function like x log x, you can define an entropy. This is really a relative entropy of the density rho d mu with respect to a reference measure mu. And this quantity is strictly positive, and you see that that's positive by Jensen's inequality. You take the integral inside the rho log rho, and it's positive. And the condition for equality in this type of inequality is that the rho should be constant, which means, of course, since it integrates to 1, it means that rho is equal to 1. So this is a very simple sharp inequality. The relative entropy is positive unless the density is just 1, constant. Okay? Now, a stability result answers the following kind of question. Suppose the relative entropy is not 0, but it's small. Okay? Does that mean that the density rho is in some sense close to being constant? Okay? That's what I mean by a stability result. It's not a kind of dynamical stability. It's not something to do with second variation being positive or so forth. It means the following thing. You have an inequality that says, well, that something is 0 or takes on a sharp value if and only if it's in some special class of functions. So the relative entropy is 0 if and only if the density is constant. Okay? If the relative entropy is close to 0, is it close to being constant? In other words, do all near minimizers of this relative entropy look almost the same? Now, there are many ways you can measure this, and here's an example. Here's a well-known, very useful inequality in the parts of statistical mechanics that I work in, and it has about, well, here are 4 names attached to it. You could probably attach more. That means it's been rediscovered many times. Very useful and simple. So that's the 2 things we would like to begin with. And it tells you that this relative entropy is bigger than 1/2 the square of the L1 distance from rho to the constant. Okay? So that's a stability result. If this tells you that if the relative entropy is small, then the density is close to 1 in this L1 norm. Okay? Now, how does one prove this kind of thing? And this is a feature that will come up in what follows. One doesn't do a variational calculation in the usual way. One doesn't look at an Euler-Lagrange equation. Rather, one finds some transformation which simplifies the classes of functionals. There's going to be reduction operation. Okay? Now, in the statistical mechanical problem that I will look at in detail, the real problem that we're warming up to, the analog of this is going to be played by certain rearrangement inequalities. And I'll explain what those are, but there's something that simplify a class of functionals for purposes of comparison. Okay? In this case, it's something really rather simple. We'd like to replace the density rho by a density sigma, and we'd like to do it in such a way that we don't change the L1 distance to the constants, but so that we reduce the relative entropy. Okay? Now, if I can find for any rho, if I can find such a sigma, then I'm reduced to looking at this inequality down here in the second row from the bottom, which has just the sigma in it. And if the sigma is from a simpler class of densities, I've simplified my problem because, well, it's a simpler object. So what's simple here? Okay, it's going to be probability densities that take on only two values. Right? So here's what you do. You take this set A, and you take the density rho, and you look at the set A where the density rho is bigger than 1. Okay? And so let P be the probability with respect to rho of that set A, and let Q be the probability with respect to the original mu of that set A. And we might as well assume that these guys are strictly between 0 and 1, or else the two measures are the same and everything's trivial. Okay? So in that case, this sigma just takes on two values. It takes on the value P over Q if the point X belongs to the set A, and it takes on the ratio of the complementary probabilities if the set X is in the complement. So this is a very simple kind of density. It just takes on two values, and if we can reduce to those, we should be in good shape. Okay? Now, one doesn't have to read all of these things. I'm just putting up some ideas here for you. And this is the same convexity Jensen's inequality. You bring the averaging under the convex function, which has been done in several of the lectures I've heard so far at this conference, and it does the right thing. Okay? So you're reducing the values. You're flattening the thing out because of convexity. You lower the relative entropy. It's just chasing through the usual bringing the average inside a convex function, and that did the right thing. On the other hand, as you look at the L1 distances, okay, the L1 distance from rho to the constant 1 is twice the integral over the set A where rho is bigger than 1 of rho minus 1, right? Because the integral of rho minus 1 integrates out to 0. So the positive parts of rho minus 1 and the negative part of rho minus 1, they integrate to the same thing. And of course, that's just 2 P minus Q. But by the same token, that's the L1 distance to sigma. So flattening didn't do anything to that. And now, if you look at what the H is, well, now the H of sigma is just a simple function of P and Q. And I remind you that P plus Q are 1. Okay, now there's some calculations up here just to show you how it closes and how simple it is. Don't try to read them, but the thing I want to emphasize is this is just now a calculus 1 problem. It's a single variable problem. There's just one variable in the game, P, because again, P plus Q is 1, and you just have to optimize over P and see which does the worst. Okay, so what we have to do is you check this stuff out, you do some variation, and what we have to show is this, that you're bigger than, that the minimal of this entropy is bigger than twice P minus Q quantity squared. Okay? So that's a stability inequality. So this tells you that this relative entropy, if it's small, you're close to the optimizer. Okay? So that's what that is. Now, this will be greatly facilitated by the fact that I'm going to talk about a special case, the simplest case of what Enrico Prezzuti was talking about in his lecture. This is the Katz model for Ising system. So the particles are not free and moving around. The repulsion is put in because things are on a lattice, and a scaling limit has been taken, and this has been discussed and introduced in the lectures of Professor Prezzuti, and I'm going to talk about this functional here, this GPL functional. I remind you it's Gates, Penrose, and Leibowitz, and it has these features in it over here. So there's a function f, which I'm going to put the picture up just in a moment. Remember, here's this term which is like the gradient term, the Cahn-Hilliard term. But when you go through the microscopic model, as was explained in Enrico Prezzuti's lectures, when you go through the microscopic model, what you get really is not a gradient term, but this finite difference approximation to a gradient term. But still, it suppresses variations. And over here, there's a double well type term. And the double well, here's a picture of it. Roughly, this is an actual graph of the real function which shows up in this particular model. And I'll tell you what that function is. Okay? If you go through the combinatorics of what this functional is, what it's representing, then there's an entropy function which, okay, just like the entropy which shows up in the previous case, here's the adding and subtracting the cross term which came up in Enrico Prezutti's lectures, and the combination of subtracting off this quadratic term and the convex entropy gives you this double well potential. Okay, so this is the functional, it's a mixture of energy and entropy, and this is the kind of thing that we're going to try to minimize. Okay, now I'm going to go through this and come right to the variational problem, because the slides have been well introduced before. This is what we're going to do. We're going to take this functional, and we've got functions on a torus of side length L, and the functions take values between -1 and 1. Okay, there are limits on the density in this case as opposed to a Cahn-Hilliard model because it's coming from occupation or holes. So -1 corresponds to a completely empty spot. It's a full density of holes. +1 corresponds to a full density of particles, and the density can't go beyond +1 or -1. It's fully occupied. So we seek to do this, and we pick a value of the constraint that the average value of this field M, the order parameter field, takes on a value strictly between these two minima. Okay? And what we'd like to do is we would like to characterize all near minimizers. We'd like to find, given an epsilon bigger than 0, I'd like to say what I can about all of the functions M, which give you a free energy which is less than 1 plus epsilon times the minimum of this thing. Okay? Now, why are we concerned about near minimizers and not minimizers? And there are several reasons. Okay? First of all, what is a free energy? When we're minimizing in these statistical mechanical problems, the free energy is a combination of two terms. There's an energy term and an entropy term. The energy term is there because, as in the lecture of Enrico Prezzutti, the underlying measure, there's a probabilistic model in the background, and it comes from a Gibbs measure. And the Gibbs measure is defined by e to the minus beta energy. Okay? There's also a coarse graining going on, and this was, again, from the lectures. We look at the thing not in terms of microscopic states of each site in the lattice being occupied or unoccupied, but you look at it on a coarse-grained level, which gives you macro states. And to each macro state, there correspond many microscopic states. So the likelihood of seeing a particular macroscopic state it depends on two things. It depends on how many microstates give you that macrostate. The entropy counts that. Okay? And it depends on how likely each one of these microstates is. And since we're working with the Gibbs measure, that determines the energy, is determined by the energy. So this is what the free energy means in statistical mechanical sense. Now, what this thing describes then, it describes the likelihood of seeing a particular state in the statistical mechanical system as it's connected up to a heat bath at a temperature beta, which is a parameter in it, which sets what's going on with the entropy. There are fluctuations in it. Because of fluctuations, you will never see the absolute minimizer. So knowing what the minimizer is not the whole story. In fact, it may not even be terribly relevant for this problem. And one has to go a little bit further. Of course, it turns out it is. What one would like to show, going back to all these near minimizers, is that everything which is sitting in this, that satisfies this near minimization condition for a sufficiently small epsilon, we'd like to know that they all look the same. Okay? Now, another reason you'd like to do this is because the actual minimizer is rather hard to discuss concretely. This problem has an Euler-Lagrange equation. I won't even write it down. It's a non-local equation. It can't be solved in closed form. So there are the minimizers, but you can't write it down. Okay? What you can write down very explicitly is an approximating family of near minimizers. So a theorem that tells you all the near minimizers look the same and gives you an explicit example of what the near minimizers are tells you everything you'd want to know about actually what the actual minimizer is. Okay? Now, this comes up in many fields. Here we are interested in finding all the near minimizers. We must find all the near minimizers because of fluctuations. Okay? But often one is looking at a minimization problem because there's a deterministic dynamical process that relaxes to a minimum of the energy. But these deterministic relaxation processes slow down when you get close to a minimum. In particular, if the bottom of the functional is very flat, the process can slow down. So what it might slow down at and be stuck at for a very, very long time is, in fact, just a near minimizer. So for many reasons, one would like to look at near minimizers instead of just minimizers, and this requires a sort of an interesting bag of tricks. Okay? Now, let's go through briefly what the thing is over here. Okay, so the free energy functional that we're looking at has two terms in it. The one up here is this guy, and remember the F is this double well potential. So when you try to minimize just that, it's really easy. If you want to minimize just this, you put stuff in the two double wells. Okay? Now, if my constraint requires that the average value of this order parameter is somewhere in between, what do? In some region, you put it in the big value. In the rest of the region, you put it in the small value, and you adjust the sizes of those regions so that you get the constraint. That's what makes it happy. But this second guy down here doesn't like the interface between the two regions or the change in it, so it would prefer everything to be constant. Okay? So when you put the two things together, there's an interesting interplay to be dealt with. Okay? And so this is what I've just said with that. So here are two trial functions which correspond to this kind of thing. One is just to make everything constant, and here's the trial function I described before. You take an m of x and you let it have the large value of these double wells, the one that's plus m beta, if you're in the region D, the domain, okay, and minus if you're outside, okay? And the other thing you can do is, right, oh, and here's what the size has to be. The size of the region, this is the D, and the absolute values is the size of it. Well, if your constraint is n, it just works out to be this. But just, again, don't look too much at the formulas because it's too much for a 1 hour talk. You just put in as much in the big value and some in the small value, and you adjust the size so you satisfy the constraint so it hits the value in between. Okay, now, right, okay. So, yeah, so here's the other quantity. Let's put these things in, and, right. So if you put a uniform minimizer in, if it's just f equals m, it's going to be just the value of m times the volume, okay? And this quantity, the compressibility, will be useful to look at here. This is the curvature at the bottom of these double wells. Okay? And so the function has a nice quadratic approximation near the bottom of the double wells. And so if you take this, use this quadratic approximation, you get a formula which looks like this. But the important thing to notice is this is a bulk term. Oops, I've got to watch out what I'm doing over here. This is a bulk term going on. Here's the thing that we're comparing it with. Okay? So this is the droplet thing that's not constant. So this is what happens when you put it in the region. Okay? So you write down the formula, and this is what it looks like. Okay? There's a difference of the 2 m beta squared. Now, let's stare at this formula I would like to look at a little more closely because it's rather, this is the key to what's going on here. This formula is measuring some kind of surface term. You see what's going on? Think of the D, this domain D, of being a droplet. That's why it's called D, is for a droplet. Think of it as a round droplet. Now the J, as in the lecture of Enrico Prezzuti, is a smearing potential of order 1. So what happens when you're looking in there, when you're integrating over this thing, you see, you're reaching across the interface, okay? So this is supported. The X is living in D, and the Y is living in the complement. The J has range 1. So this integral, the integrand, is just flat out 0 if X and Y are not within unit distance from the boundary of the region D. So it's measuring the size of the region D. Okay? So this kind of thing is measuring a surface term. The other one's a bulk term, and there's an interplay between a bulk surface and a size. Now, when the volume gets large, the surface term is going to be smaller than the bulk term, and you'd expect a droplet to form. Okay? Now, here's the next thing, is what kind of droplet would you expect to form? Okay? So one would expect it to be a round droplet. There should be some connection with the isoperimetric inequality coming in, because this is somehow measuring the boundary of this region D. Okay? Now, of course, this isn't the actual m we're putting in. This is a guess. We've put in a particular trial function. We have to consider all minimizers. But here's the here's the other really key thing which I'd like to bring out in this bag of tricks and method of looking at some things. We have to make contact to analyze this problem and to say what all the near minimizers are. We're going to have to make contact with the isoparametric problem. Okay? Now there's a standard, well-received way of doing this that goes back to De Giorgi, and it's through a method of gamma convergence. And one can, particularly if you look at the Cahn-Hilliard version of this problem, there's a way to take a scaling limit, and one probably doesn't need to explain too much about gamma convergence here in Italy. In any case, there are experts here. There's a beautiful book by Andrea Brades, who provides an excellent introduction to the subject, Gamma Convergence for Beginners, who's in the audience. So we will not be using the gamma convergence approach per se here. We'll be doing something a little more like based on what I described in the introductory example. Okay? We're going to be working directly with simplifications on a class of trial functions, and the gamma convergence approach is a way of saying that one functional that you're trying to minimize converges to another, which is hopefully simpler, and then you pass back information about that one that you understand to the functional that you're working with. So this is developed in the context of the exact functional that I'm talking about here in the book of Enrico Prezzuti. You'll find the gamma convergence approach there, and then you can pass back from information about the isoparametric inequality, which we understand, and use that to understand then why droplets, why the minimizers for this functional should look like round droplets. Okay? Now what we'd like to do is what we will do here is take a direct approach to this problem. We will work with the functional itself, and we will not try to pass via gamma convergence or limit to the functionals to the isoparametric problem, but we'll try to understand what directly at the non-local level is forcing things to be round, okay, and where the connection with the isoparametric problem comes in at the non-local level. Okay? Now, I don't know how far I'll be able to get along with in explaining this within the allotted time, and I want to get the point of view out, but this is where it departs from the gamma convergence. And I'll tell you now what I'll be working towards explaining is how this is done through certain rearrangement inequalities and the Brun-Minkowski inequality. So there's an inequality of geometric analysis, which will be coming up. It's a famous inequality, the Brun-Minkowski inequality. It's one way to derive the isoparametric inequality, and it's more directly connected with these non-local problems. So the key to showing that, here's the answer in the short version of the result of this talk, is that the minimizers, all of the near minimizers of this problem, roughly describe droplets. You've got a droplet of the right size, and it's nearly round. I'll put epsilons and deltas on this statement. It has the right size, and it's nearly round. And the thing which forces this is a stability result for the isoparametric inequality via the Riesz rearrangement inequality. Also, a stability for a certain optimal profile going across the front. And this comes out of the work of the authors listed at the front of the page. Okay, so we'd like to understand this problem. Okay, is that any question at this point, especially from students? Okay, right. So I think I've said a lot of words here, and I think I said these things here. And to keep roughly on target, right, these things get particularly interesting, and I'm gonna draw the pictures for this region over here, is where you pick the value of the constraint n. Okay? And as when we did the comparison before for the uniform droplet and the droplet which organizes it, the uniform configuration and the droplet configuration, there's a special value of the n where these two things have roughly the same size. So if you want the background, the uniform background, to have the same size as the droplet configuration, this is the region that's critical for droplet formation. Okay? So if you put the n to be too small, in other words, what happens? If you put a very small excess over the m beta in, what does it prefer to do? It prefers to smear itself over the background and just be uniform. Right? Because then it can get very close to the m beta uniformly. Okay? And if you raise it up into a droplet, you pay the surface term on the boundary of this thing, and if it's a small droplet, it pays to spread it out. Okay? Otherwise, once you start putting in too much stuff in, it pays to form the droplet. So if you're in 2 dimensions, if you make the density, which also corresponds to the size of the droplet, go like the length L. Okay, if you make the size of the droplet in a box of side length L, go like L to the 2/3, that's the critical scale. So these small droplets are a region of interest. Okay, so I have these up here on the slides, but I'm going to do it. Okay, so here's a trial function, and I'm going to put up some theorems that describe precisely what happened for this trial functions. Okay, I'm going to take a function on the torus of side length L. That's what this guy is, and will require that the guy integrate to minus m beta plus some multiple kappa, which is at our disposal. That's a parameter in this thing, L to the minus d over d plus 1. So this is this, as kappa varies, you're going up and down the range where we would expect droplets to form or not to form. Okay? And then we define this phi kappa L to be the minimum value under this constraint. So it depends on the value k that we're putting in there. Okay, and here's the deficit. This is the excess free energy, okay, relative to the minimum. So you take the free energy of some trial function, you subtract off the minimum value it could possibly have, and take the ratio to the minimum value. And then for any epsilon bigger than 0, an epsilon near minimizer is something for which this guy is less than epsilon. Okay? So it turns out, and here's where we're going to describe these functions, we're going to construct a particular class of near minimizers. So these guys come with a 1-parameter family, parameter to them, eta. Okay? These are droplets of certain size. You can think of the eta as roughly describing the size of the droplet. Okay, as it varies around in here. And if you stick these things in, we're going to show that the minimum value is equal to the minimum over these very special simple functions, plus an error which is small compared to the minimum. Now, it's not so small. One could sharpen this, but this is what's actually proved if you look at the detailed notes on the web. You can do better, but if you look at the rest of the slides, this is what's proved there. This big O thing there in the 0.22 is small compared to this one, and so this tells you these guys are near minimizers. Okay? Now this is going to be useful because these m sub etas are a very explicit value of functions, a kind of function. And roughly what we're going to say is that every near minimizer looks like them. We won't be saying what the minimizer is because it satisfies a really ugly Euler-Lagrange equation which we can't solve, but so what? If we know what these near minimizing families are explicitly, and we know that all the near minimizers look alike, we know that the minimizer, whatever it is, looks very much like one of those guys. Okay? And so this is what I've been saying. The goal will be to show that all the near minimizers look just like the right m sub eta, and the m sub eta means you just vary this one parameter, which is the size of the droplet, until it minimizes the functional. So this is a good thing. It reduces this high-dimensional variational problem down to a one-dimensional variational problem where you're just moving back and forth the size of the droplet until it fits. Okay? The shape is taken care of, everything else is taken care of, and we need to reduce, we need inequalities to reduce to get us down to that stage. Okay? So here's what these trial functions are. Okay? So you fix a volume fraction. And what this volume fraction eta is going to be is you take some of this excess mass that you're putting in the box it could be organized into a droplet, it could be smeared over the background, or it could do something much more complicated. But what the theorems will show is that these are the two possibilities you have to concern yourself with. So the trial functions are constructed as follows. You take part of this excess mass, eta, and you organize it into a droplet. Okay? You smear the rest over the background, and you construct a trial function. Now here's what this guy is, and this is sort of a sharp version of it. So you put in the value plus m beta in the droplet. The r naught is just the thing, the radius of the droplet that would be right if you were going to put all of the excess mass and meet the constraint eta in the droplet. okay? And the other is the background. Now, this sharp thing is not good enough. What you have to do is smear it out a little bit. And so here's the right thing. You take a smooth profile, because a sharp characteristic function costs you energy. And this is important. The right version is to take something like the hyperbolic arctangent function. Okay? Now, this is not an arbitrary function. It'll look like this. I've plotted the hyperbolic arctangent here. And in a Cahn-Hilliard model, it would be exactly the hyperbolic arctangent is the minimal way to go from the low-density phase to the high-density phase. So this shape, this is the instanton in this business, and the properties of this optimal front in the non-local setting have been studied by the group of Enrico Prezzuti in great detail, and this determines the so-called surface tension. Okay? So there's a one-dimensional variational problem associated to finding this optimal profile, and what it corresponds to is studying a planar interface. If you consider a region, a box, and you say you're going to be in the minus m beta off to the left and the plus m beta off to the right, and you want the density to depend only on one variable, so it's a one-dimensional problem, what's the minimum cost in free energy to do that? And that's this function over here. Associated to that is the minimum value of this free energy, and that's a number S called the surface tension, so that's part of the game. Now, the heuristics of the problem should be that what you would pay is, for any configuration, you would pay a price, which is S times the size of the perimeter of the region. Okay? Now, of course, when we're talking about these arbitrary trial functions, we don't even know if there is a perimeter or anything in it. I mean, there's this function M, and it doesn't have to take on, it's just anything. So we have to be a little careful about how to define these things. Okay, so anyway, once we've got these things, here's what's going to turn out to be the case with these guys. Okay, so we have these m etas, and so what we prove is that there's a number k star, so that when the k is less than k star, then when the box is big enough, the unique minimum is eta equals 0. You put everything in the background. It's just a constant minimizer in that case. When you go above k star, when there's this critical multiple of having enough excess mass, you form a droplet, and the volume fraction that goes into the droplet is at least as big as d over d plus 1, which would be 2/3 in 2 dimensions, meaning you never have very tiny droplets. The droplets come in always at some minimum size. Okay? Now, these kind of results there's a heuristic for this that goes back to Biskup, Chase, Katetsky, and possibly earlier. So these have been proven in other types of models and local models before, but in a non-local model, one needs a different set of techniques to do it. And so this is where these rearrangement inequalities come in. Okay? So you get droplets of a certain size, and we'd like to know what they all look like. Okay? And so what do the minimizers look like? And what they roughly look like are, well, these droplets of balls. So if you add m beta, if you lift the things up, if you remember that these things are running from minus m beta to plus m beta, if you add minus m beta to them, they look like an indicator function. And what they should look like is the indicator function of a ball of this reduced size. Okay, so it's got this the critical value of eta to the 1 over d, because we're talking about a radius now, and that gives the radius of the ball. And indeed, that's what happens. And so here's a more precise statement of what comes up. If you look at the ball, which has the correct radius, that's the thing on the right, the b with the eta k1 over d, and you look at the minimizer, where the minimizer takes a value above some threshold, and the threshold is anything not too far away from plus or minus m beta. If it's too close to plus or minus m beta, you see the details, but pick some middle value in its range, and all those should be more or less the same, and indeed, those guys are, to within a high order of accuracy, all of those level sets are balls. You can show they're stacked, but this is what proves that the droplet is round. Okay? So what this comes out of, this connection with the isoperimetric problem and the like, this comes out of the Brun-Minkowski inequality and a stability result for it. Okay? And so let me see what I want to get. Okay, so yes, classical. Okay, so there's an upper bound which goes into this, and the upper bound is a question of sticking the trial function in and doing some careful calculations. We have some explicit trial functions. The lower bound is where it's really more interesting, and I'm going to go briefly over the high spots here and focus on the role of rearrangement inequalities in this endeavor, because that's maybe the new thing from point of view which may be of interest to or useful to other people, and probably is a little different from what one might be used to in calculus of variation problems here. So at the beginning we have some trial function m, okay, and we don't have any contours or anything in it or any barrier or region or anything, we just have an m, okay, but we're going to split it up into three regions, okay, and so you take these h, so you take the value m beta and you come down a little bit. Don't worry about so much what a little bit is, and you take the minimum value and you come up a little bit, and you slice it at these heights, okay? Now the part where it's above m beta, where it's taking on the high values, that's C for the center of the droplet, if you like. The region where it's taking on the low values, B, that's the background, that's the bulk, okay? And where it's taking on these values in the middle, that's some annular region, that's this factor A, which is in the middle, okay? And we've got to figure out something about the contributions of these to the free energy, okay? Now, it'll be convenient here to remember that the n that we're considering is a small perturbation of minus m beta. It's minus m beta plus a little bit, okay? And here's the size of what that is. Okay, so now for understanding what's going on with these things, we're beginning this process of simplifying, okay? So here's the thing. So in the beginning introductory example with the entropy inequality, we took a density rho, and we cut it down to a density sigma, which just took on two values, and then we analyzed that, okay? So the key step here is to start making these kind of reductions to our trial function m, okay? So we're going to start modifying it, and we're going to modify it in such a way that it makes it simpler and reduces the free energy, but doesn't change essential aspects like the geometry of these regions. Okay, so for example, we take this m, and I define m hat, so I just cut it off at these large values and small values. Okay, that doesn't change the region where it's taking on the large values, it doesn't change the region where it's taking on the small values, and it doesn't change the region in between. So the essential geometry of the trial function has been left the same. Now, since I've cut it off top and bottom, I've reduced variation, so that reduces this Cahn-Hilliard term, it makes it smaller. That's just like what we were doing with this entropy thing in the middle. Okay, now likewise, if you take this free energy thing, okay, and you go around and integrate it, this guy just splits up into these pieces, and in the annular region, remember we're just cutting things off top and bottom, so the part coming from the annular region is the same as the m is equal to the m hat there. Okay, so here's what we do. We take the free energy, we throw away a bunch of the pieces, we keep a part that's the surface contribution, which comes from just integrating over the annular region. This is the transition region where it's going from the large values to the minus values. We're going to keep just that in our lower bound, and you have to keep the bulk part in the background. But this guy here, we have the simplified guy, which is cut off and does this. Okay, so we want to estimate these contributions, and an interesting thing that comes up again is now showing that, well, they've really got to look a little bit like what we think they look like. And let me put up a picture here, which is probably the best thing to do. I'd like to show that the set C, where they take on the large values, is not empty. So I've got the proof up, but that's okay. Let's make a change of variables. Introduce omega to be m, take away the constrained value of the n. Now, since the m integrates to n, the omega integrates to 0. Since we're just subtracting off a constant, the energy term here is the same. Okay? And so if I introduce this function script g, this is a new free energy functional which has this g in it. What's the g? Okay? Here's a construction that's familiar. It comes up in all this kind of stuff. We take this tangent line approximation. G of w is the function f of n plus omega minus f of n minus f of n times omega. Now, n's a constant, and omega integrates to 0. Okay? So for that reason, the free energy of a trial function m is equal to the free energy of the trial constant guy plus this g gadget. Okay? And now, here's the thing. Suppose your trial function m has a better value than the constant density trial function. Then this function script g has to be negative. But when can the script g be negative? Well, it can't come from the first term. It has to come from the second. And here's a picture of what this g looks like. Since we subtracted off a tangent line, it tilts it down. Okay? And so any trial function that is going to do better than the constant trial function has to get into this region over here where it's getting close to the second minimum. So there will be, in anything that's going to give you, I mean, it can't sort of get halfway up and then go down. I mean, that sounds unreasonable, but this is how you prove it. By making a change of variables in the functional, if it's going to do better than the constant, it has to go all the way up to the plus m beta region, and so you will have this annulus, you will have the C, this annulus will be non-empty. Okay? Now, I'm going to skip over the next couple of slides, but you analyze these things separately. The bulk contribution is just pure convexity. It's just Jensen's inequality. And what you do is you use Jensen's inequality, and you see that in your region where it's taking on these lower values, you get just what you would from our trial function. So it matches what you'd get from the trial function, which is constant out there in the bulk region. And Jensen's inequality says, well, anything's going to do a higher free energy than the constant. Okay, so the bulk region is relatively simple. What's much more interesting is the surface contribution. And we'd like to, so there's a lot of stuff up here, but here's what I want, here's what's going to be shown. Now, this is hopelessly detailed, so let's simplify this. This is the contribution from the annular region. And there's a 1 minus the big O. Well, the stuff in the big O is junk, so forget that. Then there's this dB. Now, B with absolute values on, that's the volume of the unit ball, and D times the unit ball is the surface area of the unit ball in D dimensions. Here's the reduced fraction of this guy to the D minus 1 minus some small number. So what this is the surface, what this factor is that's after the sub plus is the surface area of a ball of the size that if you put everything in the ball, but you instead of putting everything in, you put a volume fraction eta. That's what the eta to the 1 over d is doing. Okay? And then there's 1 minus some junk, so forget about that. But the very last thing I want to pay attention to, that's the S. Okay? This S is this key number, that's the surface tension. And that's what came out of this one-dimensional, the instanton problem. So you solve the one-dimensional problem, and it gives you a specific number for what the surface tension is, what the cost of going from the minus m beta region to the plus m beta. And you've got to get that number out for the heuristic. So we care about that number, we care about the size of this thing, and that's what this thing should be. So at this stage, what we have is just we know nothing about the set. We've taken a general function m. We know somewhere it gets up to these large values. We cut it off top and bottom, and we've somehow got to get a ball out of it, and we've got to make contact with this one-dimensional variational problem which defines S. So how do you get back from this thing which could have any weird kind of shape at all to the one-dimensional problem that defines S? You've got to get a one-dimensional, you've got to reduce to a one-dimensional trial function. Okay? And this is what's done with the Riesz rearrangement inequality. Okay? Right. So we need to replace the minimizer by a radial function, and here's what that is. Okay? So, yeah, I'll be able to right. So the Riesz rearrangement inequality is the following thing. You take a function, and you slice it up like a layer cake, okay, into all these pieces at different heights. You take each slice of the function, and you rearrange that into a ball of the same shape. Okay? Let's put a star on that. So that's what's indicated with this indicator function. So 1 sub braces f bigger than lambda star means you take, well, 1 means the indicator function of the set where f was bigger than lambda. Putting a star on it means you take that set and you just transform it into a ball of the exact same size, exact same volume, and center it at the origin. Okay? Now, if you stack all those guys back up, which can be done with that integral, you reproduce a function which has the same distribution function, so its measure, the measure of its level sets is the same as the original guy, but they're all organized into balls. Okay? So you've turned an arbitrary function into a radial decreasing function. Okay, so that's what this thing is. And you've preserved the size of all the level sets. Now, the last chapter of the Hardy-Littlewood polyclastic text on inequalities is devoted to rearrangement inequalities. And the main theorem in there, the longest proof in the whole book, is the proof of this Riesz rearrangement inequality theorem, which is this. And so this is what the Riesz theorem says, and it looks reasonable. So take three non-negative functions and perform this convolution integral. So if you like, you're convolving g with h and integrating against f. That gives you less than or equal to what you get if you rearrange the guys. So if you sweep all the stuff together and bring it all into centered balls, that gives you a larger quantity. Okay? That's what the Riesz theorem says. Okay? So what we're going to need to do here is to look at the cases of equality in this. Now, right, let me remind you here, if I've got the functional up, I hope this is, let me just look ahead. Here is this. Okay, well, we can do it from here. Now, what are we going to do? Where are we going to apply this? We're going to apply this to this integral. Remember, and you've got the m of x minus m of y squared integrated against j. Okay? There are two terms there. One is the m squared, m of x squared integrated against j. That's just the integral m squared. But the term that's subtracted off is m of x, j x minus y, m of y. Okay? That's exactly of this type. So think of the f of x as the m of x. Think of the h of y as the m of y, and think of the g there in the middle as the j of x minus y. This is the term that's subtracted off in this Cahn-Hilliard term, the non-local Cahn-Hilliard term. Now, the Riesz rearrangement inequality says that that thing that you're subtracting off is going to go up when you rearrange stuff, which means you're going to decrease the Cahn-Hilliard term, because the stuff on the endpoints is left alone. Okay? So the rearrangement gets you down to a radial problem, okay? And once you've got the once you've done the rearrangement, then, well, you've decreased, it's gone in the right direction, okay? And the question that comes up is, how much did you lose in doing this? So once we've done the rearrangement, now we've got a function which is a radial problem. We can make contact with the single variable optimization problem, because now your trial function has a nice structure. It's going out from the origin, it's plus m beta. It makes a transition over some profile out to the minus m beta, and you can compare with what it costs the instanton to do that. So this is why the s comes into our problem, because we've done the rearrangement and made the contact. And if it doesn't have the right shape as it goes across that boundary, you pay too much and you pay more than s, because s is the minimum. So it's got to go across and have just the right shape. Okay? But now what does that tell you? That tells you that the rearranged function must be a droplet of the right shape. Okay? What about your original m? What did that look like? Okay? This is where it comes into the stability question, because when you do the rearrangement, you lose all information about what the original configuration looked like. Okay? So what we need to know, we need a theorem which tells us that when you do this rearrangement, you lower the value a lot unless you were already pretty close to rearranged. Okay? So once we know that, since we know the rearranged thing looks like a droplet of just the right size, and we know that if we didn't lower this value a whole lot because that would cost free energy, well, then the original function must look like the rearranged thing. So what we need to know, what we have to have in here, is a theorem which tells us that when you do this rearrangement inequality, that if the value doesn't drop by a whole lot, then you already were pretty close to rearranged. Now, the Riesz rearrangement inequality is extremely subtle, and the cases of equality in it were analyzed by Almut Burkhardt, who's a student of my colleague Michael Loss, and she wrote a nice, there are lots of cases of equality. However, we're in a special case here because this middle function g is the potential function j that's been in this lecture and the lectures of Enrico Prezzuti, and it's a radial decreasing function. And in that case, there's a theorem of Lieb which tells you something more. Then the cases of equality are very strict. So if one of the functions is already rearranged, and it has lots of balls as its level sets, okay, then what happens is the only way you get equality in here is if your function was already radial, it was just centered on some other set, and all the rearrangement is doing is translating it. Okay? So what we do in this work here is to, in the last part of this work, with which I will wrap up, is to prove a stronger version of Lieb's theorem, which says that, in fact, if the value is close in this thing, then it acts almost by a translation. Okay? And what that goes through is a nice connection between this operation and the Brun-Minkowski. And I'll just show you a couple more slides to give you the flavor, because the time is about up, and this will make contact with things that may be of interest and use to you, but I won't try to go through all the proof of what that is. But you see what this is going to do for us. We use the rearrangement operation to reduce a high-dimensional problem to a one-dimensional problem. Then we can analyze the rearranged gadget, because it is one-dimensional, and we can learn everything about it. But we want to know about the original function. So we need something which tells us that the rearranged guy, which we understand, looks just like the guy we started from. And that's the theorem we prove going through the thing. Now, let me tell you the last details about this thing here to do it, because there's some interesting stuff and some new things we've just figured out. There is no rearrangement inequality on the torus. Okay? The Riesz rearrangement inequality I wrote down was on Rn. And indeed, it's closely connected with the isoparametric inequality, and if things wrap around, you don't want to rearrange them on the torus. So what we have is some kind of droplet in our configurations, and to apply the rearrangement inequality at all on the torus or with any other kind of boundary conditions, what you have to do is to show that it can't. So remember, okay? So this torus, the boundary of the torus, is periodic. You can slide it around. So what we call the edge of the torus, we can use translations on the torus to move it wherever we want. So it could be that the edge of the torus came in the middle of the droplet. That would be bad. But you can't have a large intersection with a strip close to the boundary on too many pieces, because then you would have too much mass in it. You would violate the constraint. So you take the region where it has large values, you slide things around until you've got just maybe some arms poking out on a couple of sides, and you cut it at those places. And this is the nice thing about this free energy function, which doesn't have the gradients. You can do the cuts at a small cost. Okay? So we maybe increase the free energy a little bit here, but then we can erase the edges right here and extend the function at this level that we called M- out to infinity in the plane, and now we're sitting in the plane and can rearrange. This is a crucial thing to do, and this was easier for us to do initially only for these small drops in the critical scaling regime. But lately we figured out how to do it for large drops also. It's a little more complicated to do the cutting, but this is what enables you to go from the from the inequality on a torus where you can't rearrange to rearrange. Okay? Now let me just put up what this Brun-Minkowski inequality is. Right. So, and I'll finish with this. So this is understanding the key to this geometric inequality is what enables us to make contact with the isoparametric problem in this variational problem. So if you have two sets in Rd, the Minkowski sum is the set of points x plus y, where x is in E and y is in F. Okay? Now, it's a little tricky what this thing is. If you change these things by a set of measure 0, if I add a point onto F, it's going to make E plus F be very big. Okay? But this is what that guy is. Okay? Now, it turns out, and here's where it comes to the thing with convolution. Let me skip this thing. So if you have nice sets, and I'm skipping over what nice exactly means, it's easy to see that the Minkowski sum is exactly the support of the convolution. Okay, so one has to be careful with this, again, because sets of measure 0 matter when you're doing Minkowski sums, and this is the beginning of a connection with the convolution inequality. Okay? Now, what the Brun-Minkowski inequality itself says, let me go back to well, okay, let me just tell you what it says and finish up with this thing here. So the Brun-Minkowski inequality says that if you take these two sets, E and F, Okay, and you scale them. So you take t times f plus 1 minus t times e, and you look at the dth root to the volume of that. So why the dth root to the volume? It's like a length. Okay, then this is a concave function of t as you vary it back and forth. And taking the derivative of this concave function when one of the sets is a ball gives you an estimate on the surface area. This is a classical argument going back to Minkowski. It's called the Minkowski content of the surface. So the Brun-Minkowski, the strict convexity which is in there, gives you the control on surface area, which is what we're after, and this is the connection with the convolution in this inequality. Now, the Brun-Minkowski inequality has a unique status among inequalities for the following reason. It's the only one I know of where the names on it, the second name attached to it is for the person who settled the cases of equality. So Brun proved the inequality. Minkowski showed there was equality exactly when the two sets were homothetic. So one's a translation and a dilate to the other. Okay? The general story of a stability inequality for Brun-Minkowski is not known, but what Francesco and Maggi and I have recently proved is a stability result for Brun-Minkowski when one of the sets is a ball. And that's what's important for controlling the surface area. And so using stability for these geometric inequalities, Brun-Minkowski, enables us to go back and say that, okay, when you replace this trial function by its rearrangement, you lower the free energy by a heck of a lot unless it was already pretty much rearranged anyway. Therefore, near minimizers have the shape you expect. Okay, so I think I'll stop there. I think I've hit most of the high spots, but of course, I haven't been able to dot I's and cross the T's, but this is the main ideas going into this way of looking at this near minimization problem. So thank you very much. Mm-hmm. Yes, uh-huh. Right. Mm-hmm. So we've discussed this a bit with Francesco Maggi in particular. So it's conceivable, but certainly not done and not completely clear how to do it. But one could have a similar sort of rearrangement into profiles with, so instead of rearranging the functions so that the level sets were balls, they would be appropriate versions of the wolf shape. And one could do, the Brun-Minkowski, as I've stated, it's a theorem for general sets, right? And you could do it for anything. And so then one would need, again, a specialized version of the Brun-Minkowski where one of the sets was the wolf shape. Now, as we do it currently, we use, so how do we get this stability for the Brun-Minkowski? We leverage some results which are known. We go back to the isoparametric inequality because you can integrate up along balls. There's an integration formula. The corresponding thing for the wolf shape is known. There's an isoparametric inequality for the wolf shape. So it's quite conceivable that one could do this indeed for the wolf shape, and it's something that will be investigated. But and that's one thing I like about these problems. It raises the subject matter, this mathematical physics problem, leads one to consider problems in functional analysis and geometric analysis that are very natural inequalities, like stability for Reese and so forth, just come up at the heart of the matter. The analogs, when you move away from balls, are at least as interesting, and they certainly deserve a close look, and we'll get one. What we had been concentrating on most recently was, again, though, this issue of how to do the cutting when the droplet is large, because then you can have more stuff around the edges, and then it's more complicated to get off of the torus onto RD, where you can even do the rearrangement at all. But the wolf shape question is extremely interesting. Yes. Mm-hmm. Yes. Right. So what happens so let me go address the first one and come back to that. These come from, in the isoparametric inequality, in dimension 2, one could probably get a very high P, but 2 is very special because in 2 dimensions, so when you do isoparametric problems, an L infinity control would be controlling how stuff is sticking out. You have to catch filaments. And so in 2 dimensions, if you have a filament reaching out for a large radius, it costs a large perimeter to get out there, and this is expensive, and there's a bonus in inequality which gives you a strong stability here. So to use, when you do isoparametric inequality in 3 or more dimensions, people use an L1 control because it's really all you can do. You could have a thin arm coming out. So this way we measured the set, you took the characteristic function of the ball and the characteristic function of the level set, and you slide them back and forth and get the best fit in the L1 sense. That's really pretty much optimal for any kind of isoparametric thing, because also with this free energy function, you could have a tiny little filament sticking out, right, that's very thin, and it wouldn't cost free energy, it wouldn't cost surface area, a piece of spaghetti coming off of your ball in 3 dimensions, and so you have to allow for those kind of things. And so this kind of L1 measure of how far away you are from a ball, it has a name, it's the Frankel asymmetry, and it's what's used in all the work in isoparametric stability in more than 3 dimensions, 3 or more dimensions for that reason. Now, the exponents is a very interesting issue, and a recent triumph of Italian mathematics, I would say, is getting the exponent down to the optimal one in the isoparametric inequality itself. So if you look at the excess perimeter, and there's a lower bound on the excess perimeter in terms of this asymmetry, right? So there's a lower bound on the asymmetry in terms of excess perimeter. So if I have some excess perimeter on my set, and I want to know how far away it is from a ball, there's a lower bound. The exponent on that quantity, the asymmetry, the L1 distance from the closest ball, has an exponent 1/2 on it now. And this is work of Maggi, Fusco, Pratelli, and in the quantitative version, Alessio Figali has contributed to this. So it's rather recent work, and before that, the best known was 1/4, and the 1/2 is sharp. When we do the analogous result that Maggi and I have for the Brun-Minkowski inequality, at this stage we get an analog of the 1/4 result instead of 1/2. And then when you piece this together through the convolution to get back to the Riesz theorem, we lose another factor of 2. So the eighth comes from this, but in principle it could get down to 1/2 or something. It does not depend on dimension, right? It's a dimension-free thing, as it is in the isoparametric inequality itself. Okay, so this one of the really beautiful series of papers written is dealing with this isoparametric question and showing that the exponent is 1/2, the corresponding thing, the distance to the closest ball. The exponent in the asymmetry there is 1/2 for all dimensions 3 or more, 2 or more. In fact, it applies also in 2. In 2 you can do better things though, because it's the bonus in inequality. Okay, well, thank you very much.
So thanks for this presentation. In fact, I give 2 talks, maybe 1 hour each. So one is over dynamics, the other over fatigue, and maybe it's better that begin by dynamics and then by fatigue. It's more natural, I think. So it's so to complete your presentation. So I use variational approach, but you will see that in dynamics, it's a crucial point to see if the our variational approach is a good one. So the key point of this presentation is to see when we will see in an example that the crack can evolve in time with discontinuity of the length in time. And so if you use quasi-static approach, no problem. You can assume that the length of the crack is discontinuous. Our formulation allows that. But the problem is to see if our solution, our variational solution, is a good one. And one way to see if it's a good one is to compare with dynamical solution. And so my presentation consists in first present the quasi-static approach based on minimization of energy and to compare to dynamical approach in the case where there is a jump of the crack length. So I only consider a very simple example. So you have to understand this example, which is in this picture here. So you consider a film, a thin film, and I will assume that this film has no bending energy, so it's like a string, in fact. And I neglect the extensibility. That means that I assume that the length of the film is always the same. I consider only small displacement, and I consider that the tension here is constant in time. So I prescribe the tension of the film, n, and in the sequel in my calculation, n is equal to 1. I consider the units, I choose the unit of in such a way that n is equal to 1. So n is fixed, and I prescribe the vertical displacement of this point, of the end of the film. And I will assume that this vertical displacement depends on time like that. So capital T is the opening, is the displacement, small t is the time, and I assume that there is a constant speed to open this, to peel this film. In quasi-static, epsilon is simply a parameter, and in dynamics, it will play an important role. So this film, at the beginning, it's perfectly bonded on the support. And I assume that there is glue, and that this glue is characterized by some toughness, which can depend on X. So I will use Griffith's assumption on the energy. That means that to debonded length, a small length of the film, I need a surface energy which is proportional to this constant here. But this constant here can change from point to the other. And the key point is to consider what happens when I have a jump of k on some interfaces. And if I have jump, I can consider a jump from k1, which is less than k2, and k2, which is greater than k1. And we will see that it's not the same when there is an interface where the toughness becomes larger, or in interface where the toughness becomes smaller. So I will consider this problem in quasi-static and then in dynamics, and that compare the solution. It's okay for the problem? So, all is a story of energy. So I have to compute the energy of this system, first in quasi-static, then in dynamics. So I begin by quasi-static. So I recall simply the picture, and I will define three quantities: the potential energy here, the surface energy here, and the total energy, which is the sum of this energy. To compute this one, I recall simply. It's elementary in my situation where I am in small displacement context. I neglect the extensibility. I neglect the bending energy. So the unique potential energy is due to the work of the tension here. So it's simply this quantity, the work of the tension in the horizontal displacement of this point here. Because of the inextensibility, you have a relation between the horizontal displacement and the vertical displacement. And because I am in small displacement, in fact, the true relation should be this one. You can see. So the true inextensibility condition is this one, and I neglect this term, which is not of the same order as this one. So the vertical displacement is small, the horizontal displacement is of the second order, and this one of the fourth order. So I neglect this term. And I find this expression for P. Since U1 is equal to 0 at infinity, I can define P by this integral here. Now, so it's for a certain configuration of the field. If I consider that the film is at equilibrium, when I have dependent the film on the length L here. So in this case, the equilibrium is given is such that, in fact, this integral is the minimum among all the possible configuration of the film, and I find simply, it's a straight result, it's an obvious result, that the position of the film is simply a straight line here. That means that U prime 2 is a constant here. And because of the boundary condition, we obtain this quantity. So it's an equilibrium configuration. I compute the potential energy, and I find this quantity. And then the other important quantity with Griffith's theory is to compute the derivative of P with respect to L for a given T. So I fix the boundary condition. I consider a growing of the quark, a virtual growing of the quark, and I compute this derivative. Obviously, this derivative is negative. The film releases some potential energy when the quark propagates, and I find simply, it's a trivial computation, this quantity. And you see that G is a decreasing function of L for a given T. For the surface energy, is completely trivial because in my case, K, yeah. Why? What energy? T is it's in one dimension. N is the forces. Obviously, one dimension, one length is missing here. It's some thickness of the film, if you want. So one dimension is missing, but it's a constant. It's not important. So, and in fact, N is equal to 1. So there is no problem for that. one length is missing in this expression, but they do not play a role. So we consider this energy, and for the surface energy, if you know K of X, you can compute the surface energy, which depends on L. For instance, if K is constant, the surface energy is simply proportional to L. So I can compute the total energy of the system as the sum of these two terms. So now, I can use this Griffiths theory, even if I am not exactly in static, but only in quasi-static. Quasi-static means if I assume that the displacement at zero is has a speed which is very small, I can consider that the kinetic energy is negligible, and I consider that the film is at equilibrium at each time. Okay, so it's a quasi-static assumption. So if I use Griffiths theory, I have to solve this problem. Maybe you are not familiar with Griffiths, and it's necessary that I explain all the lines. The first one is the irreversibility condition, which means that the quark, once I have debonded the film, I cannot bonded this part of the film. So L dot must be positive. The second line is the Griffiths criterion of propagation. Griffiths say that the quark, the film can debond only if the release of the potential energy is sufficient to create new surface energy. And so he says that at each time the energy with weight must be less or equal to the toughness, to the surface energy density K, which can depend on the position of the tip. So it's a characteristic of the position of the tip. And he says that the propagation appears only when I have exactly J equal to K. So this condition, it's an energy balance, which says that when the quark propagates, the energy release rate is exactly equal to the surface energy that I have created. And so I have to solve these three conditions, two inequality plus inequality. It turns out that this formulation is valid only, obviously, only if L is smooth in time. So by construction, I cannot consider with this formulation discontinuity in time evolution of the length of the quark. Is this solution as always? Is this problem as always a solution? The key point is this property. So we can prove. You can prove this property in this paper here. It's a fundamental property which is true not only in my case, but when you consider Griffiths theory with one variable for the length of the quark. So the theorem says the following. If I consider proportional loading in my case is simply capital T is increasing. So I am in this case. I find a solution of this problem, which is continuous in time, if and only if, so in the interval of time, T0 to L1, where L will go from L0 to L1, if and only if this ratio here is a strictly decreasing function of L. What is this ratio? You see that it's the ratio of the energy release rate, which is calculated for a unit load. So you take capital T, if you want, equal to 1, or T equal to 1, it's the same, and you compute this quantity. In my case, it's very trivial. This quantity is given here. So I consider that capital T is equal to 1. And I divide by the value of the toughness at the tip of the quark. So I obtain a function of L, and if this function is decreasing, there is a unique solution to this problem, which is continuous in time. And this ratio is simply the energy release rate by surface of energy criterion. And this function must be decreasing. If not, no solution to this problem. But you see, there is no solution in the sense that necessarily I have to consider discontinuity in time evolution of the length of the quark. But in your case, what happens? G, you see that G is a decreasing function of L. So it's good. But depends on the evolution of K in terms of L. So if I have a discontinuity of K, where K decreasing at one point for K2 to K1, I will have a decreasing of small g. And so this theorem says, in that case, I cannot obtain an evolution which is continuing in time by using Griffith's law. So, in essence, I say the same thing here. So what I have to do? I have to change either, I say, I consider that discontinuity in time is not quasi-static evolution, and I consider the dynamical problem. Good. I will make that at the end of my talk. But I can also try to change Griffith's law by another law. In fact, for engineers, it's important to propose only quasi-static approach, because solve the problem in dynamics is very difficult. And so if I can't find a criterion to find the discontinuity evolution of quark for the engineer in quasi-static is better. So I propose to do that. So I recall Griffith's law, in my case, is this one. First of all, I will change this equation here. So this equation is, in fact, balance of energy. This term is G, the energy release rate. This term is the density of surface energy. So if I consider the total energy as a function of T and L, which is the sum here of these two functions, you see that G is minus dP over dL, and K is the derivative of S with respect to L. And you see that this line is nothing but that this equality here, the derivative of the total energy with respect to L multiplied by L dot is equal to 1 at each time. What? It's equal to 0. It's equal to 0, yes. So you replace simply here you have J minus K is equal to 0. So I write this equation, and you see that this equation, it's like that. But you see that you have the partial derivative of the total energy with respect to L. So you can write that as the total energy of the derivative of the total energy with respect to T, the total derivative. Sorry. And simply I subtract the missing term, which is this one. Okay? So this quantity is equal to this one when the evolution is smooth in time. Sorry, sorry, it's exactly this one. And so I have simply to integrate in time this equality. So integrate in time, I obtain that at time t minus E at time 0, and in my case, the energy at time 0 is 0, equal to the integral of that. Sorry, so you change, you simply change the t, I call the variable s and not t, and I obtain exactly this line. So that means that this line is the same as this one when L is a smooth fraction of time. So it's the same thing. It's the balance of energy which is written in a different form. But remark that, and conversely, if I start from that, I obtain that, and by taking the derivative of that, I obtain that. So it's equivalent when L is a smooth fraction of time. But obviously, I can use this relation even if L is not a smooth function of time. I have to, because I can evaluate this quantity at each time. There is no derivative or something. And this integral, even if L is not smooth in time, I can compute this integral. And so I have another form of the balance energy which allows to consider non-smooth evolution of the length of the quark in time. So it's mathematics. Mathematics is good, like you say, but physics is better. What is the consequence of that? In fact, the consequence of that is continuity in time of the total energy. So I try to introduce a principle. If the quark is discontinuous in time, it's not a problem. We will have continuity of the total energy in time. That means that even if I assume that at time t, the length of the quark jump from L0 to L1, there is some release of the potential energy. It's not a derivative. It's a finite quantity. And this release of the potential energy is exactly equal to the surface energy which is created. So it's energy balance which is generalized in the case of discontinuity of the quark. So first proposition, I replace that by that. But it's a physical principle. It's a physical assumption. And one goal in the second part of my talk is to see if by considering the true dynamical problem, this result is correct. The other part of the change is due to the fact that, so, in the situation where small g, so the ratio of capital G over K, is a decreasing function of L, I have existence and uniqueness of a smooth solution. Otherwise, I have no more solution. So I try to extend the formulation of the problem to obtain discontinuity in time, discontinuous in time solution, but by making that, in fact, I will find that there is an infinite number of possibilities. So I have to add some criterion of selection of solution, because by considering non-smooth solution, there is an infinite number of possibilities. And for that, I introduce a stability condition. In fact, stability condition is written here in this form. here. And I explain that. It's simply an extension of this inequality. So you have to understand that. So I start from LM, this one. So in LM, I say that the true length of the quark at time t must have an energy which is smaller than the energy of the quark at the same time t with the length which is greater than the true one, but in some interval. So it's a local minimum principle by only considering greater quark. Why I only consider greater quark? Because the reversibility conditions say to me that, in fact, the system can only explore quarks which are greater than the real one. And so I compare the energy for greater quark, and I write the stability condition with this inequality only valid in this interval on the right of the true length of the quark. By doing that, you see that simply I can deduce from that this inequality. In fact, it's simply you have simply to consider small l, which is this one, plus some small constant here. So in some interval, so it's not the same age, in some interval, I have this equality. So if I divide, so I consider that, I divide by h, and I pass to the limit, so it's in this sense. So and I pass to the limit when h goes to 0, h is positive. In fact, you see that I will obtain simply the derivative of E with respect to L, which at t must be positive. But here, what is this? The total energy is the surface energy plus the potential energy, so it's simply K minus G. And so I recover that. That means that Griffith's criterion is nothing but a first order stability condition. And I simply propose to enlarge the stability condition by not only considering the first order stability condition, but other order. And so I enlarge the stability by that. And so our work with Gilles will consist in the reinforcement of that by considering global minimization. And so you replace this inequality in a small interval by this inequality for any L greater than L of t. So this is the principle of global minimization. It's the principle of local minimization. It's simply a reinforcement of that. So this is Griffiths, but a new Griffiths with a stability condition and a new form of the energy balance. And we can now find solution to this problem. But unfortunately, there is an infinite number of solutions to this problem. So, how long? 15 minutes. Okay. One possibility, one solution. I explain one solution. I explain two possibilities, and we will compare in dynamics what we obtain. So, for instance, a possibility of solution which respect all the conditions above, but we discontinue in time, is the following. So I assume that the toughness is K2 first and K1 then, and K2 is greater than K1. So with Griffiths, I have no continuous solution in time. So a possible solution is the following. If I consider global minimization, for instance, the evolution of the quark with global minimization is the following. First, I debond the film by using classical Griffiths law, G equal K, until a certain length of debonding L2 T star here. Then the quark jump to another length L1 of T star, and then the evolution of the quark is always given by classical Griffiths law. So there is a jump at this value of the displacement here. And why it's possible to find a jump at this time? Because if you consider the total energy as a function of L at this time, you find this picture. You have two minima here at the same level. And you can, if you consider global minimization, you can, this point is a global minimizer, this point a global minimizer, and you can jump from here to here. But you see that this jump is before the quark has reached the interface here. And so you have a jump of the quark, so the film propagates, the interface is here, so the tip of the film cannot see that the interface is here, but if you compute the total energy, it's better to go here, and so the film jump from here to here. It's given by global minimization. Because capital T star is exactly the good value of T at which that happens. So other picture of the total energy for different value of T. So you have the total energy as a function of L at different T. You obtain this picture. When T is small, you have only one global minimum here. When T is larger, local minimum appears here, and so on. And at this time, at this particular time, absolutely, absolutely. And you continue, and you have the converse. The local minimum is here, and the global here, and so on. And so I give this picture only, but all the pictures are important, in fact. Okay. Sorry. So it's one possibility, which is global minimization. It's not what is given by dynamics. What is given by dynamics, in fact, is this solution. So I explain this one. This one, so the interface is here. I debond the film. It follows the classical Griffiths law, G equal K. G equal K2. When the tip of the quark reaches the interface, then there is a discontinuity of the toughness, and there is a jump of the quark. And the quark will jump from here to here, and the length of the jump is given by energy conservation. So I obtain this value by writing that the energy after is equal to the energy before the jump. Conservation of energy. By doing that, in fact, if you compute the energy release rate, the derivative of the potential energy at this point, is smaller than K1. And so the quark will stop. So there is a jump, a stop, and you increase the opening here, and you increase the energy release rate. And when G equals to K1, the quark starts again. And then follow classical Griffiths. So in fact, a possible solution is the following. Classical Griffiths until the interface, jump with continuity of the total energy at this moment, an arrest of the quark, and the quark starts again when the energy release rate is large enough, and then the quark follows the Griffiths law, the classical Griffiths law. And it turns out that in this situation, dynamics give exactly this result. In fact, not exactly this result, but at the limit, it gives this result. And I will try to explain dynamics. All the beginning is quasi-static. Yes. But for that, I have to define what is the dynamical problem. Yes? So, a lot of new definition and new, but I will explain the essential of the formulation. In dynamics, so now I reintroduce that the real time. And the real time, so I prescribe the displacement at the end of the film with a constant velocity, which corresponds to the parameter epsilon. Okay. The evolution of the quark is given by Griffiths law, but Griffiths law in dynamics. What is the difference between Griffiths law in dynamics and Griffiths law in quasi-static? The difference is in the definition of the potential energy release rate. This quantity in quasi-static is simply the derivative of the potential energy at equilibrium with respect to the length of the quark. In dynamics, you can define the energy release rate by path integral. It's one possible definition. I give this one here. If you know Rice integral, in fact, it's Rice integral in dynamics where simply you consider not only the potential energy, but also the kinetic energy here. So, this path integral, the path integral where you have to compute the kinetic energy plus the density of potential energy. So N1 is the normal of the first component of the normal of the path. Here is the stress vector, and here is the derivative of the displacement with respect to x1, which is the direction of propagation of the quark. In our situation, in one dimension, with the film, you have simply to use this formula where W is this density of potential energy. Sigma is simply the derivative with respect to U prime, this is N times U prime. The path integral is simply the points. You consider a point just before and the point just after the tip of the quark, and the normal is plus or minus 1. By using that, you see that, simply a simple computation, that you obtain that G is given. So you have debonded the quark, the film, until this point. After that, it's glued, and so U is and U prime and U dot, so the slope and the velocity are equal to 0. And G is simply, so what appears here is the jump of U prime square and the jump of U dot square, but the jump of U prime square is simply the value of U prime square just before, because just after is equal to 0. And so you have to compute this quantity here, and if you compare with the situation in quasi-static, in fact, this term in quasi-static disappears, and this term is exactly the term that we have computed before. So in quasi-static, so the fact that I consider dynamics, I change the definition of G, so kinetic energy terms appears here, and obviously the evolution, the configuration of the film is not the same, it's not at equilibrium at each time. In fact, what appears in my situation is the following. To find the solution, in fact, you have a film here, it's glued until here, and because of the boundary condition here, where you prescribe a constant velocity, here at the beginning, the film is glued, so u and u prime and u dot are equal to 0. So you have a misfit between the boundary condition and the initial condition. And so you have shock wave in the sense that u prime and u dot are discontinuous in space and time. So you have this type of discontinuity which evolves inside the film. The discontinuity of u prime simply says that you have a kink, in fact, in the film. So you have such a discontinuity of the slope, and this discontinuity propagates in the film. So at another time, you will see this configuration. And the velocity of propagation is given by the velocity of the wave. In our case, the velocity of the wave is given by that. The tension divided by the density of the film. So we have to solve all of that. Wave equation, boundary condition, we have to consider jump of the slope, jump of the velocity, and in fact, we can solve the problem. And it turns out that the dynamical Griffith's law admits a unique solution. So in dynamics, I have not to change to add some properties. Only with Griffiths, at least in this situation, I have a unique solution. And this solution is given by solving the motion of waves inside the film, which interact with the propagation of the tip of the film. We can do that. So we have to write jump condition, the energy criterion for the propagation of the quark, and we find the solution of this problem, which admits a unique solution. So I simply explain what happens in the case where the toughness is first K2 and then K1. So I explain the result. Now, and I will compare with my quasi-static one, and the conclusion will be that the second solution quasi-static that I propose is a good one. It corresponds to the limit of dynamics, okay? I claim that, but I claim more. I claim that in this situation, dynamics said that the good solution is also quasi-static and given by conservation of energy. Two things. I claim that we have to make dynamics, okay, but it turns out that dynamics says that quasi-static is also correct if I use the good criterion. Yes. Yes, but it turns out that at the limit, this jump is instantaneous, in fact, and kinetic energy plays a role only. So I continue, maybe you will understand. So the solution is the following. In dynamics, I solve the problem in dynamics. First, the velocity of the debonding is constant. It's given, you can see here, this quantity. So it's the velocity. So I have rescaled the time. Sorry. The time is rescaled, and what is the, I consider as that all functions are function of capital T and x. And capital T is epsilon small t. So I consider that the good variable is, in fact, the value of the displacement, not the real time. So it's a rescaling of time if you want. And all is given in terms of capital T. So the dot is a derivative with respect to capital T. And so there is some epsilon between the quantity. So the velocity of the quark, so dl over d capital T, at the beginning is a constant. It's a constant which is given by that. Where appears the speed, some quantity. So I have take as one some physical quantity. So no problem with the units. There is no real problem. So if the speed of the displacement is small, you see that these terms converge to 2k2. And this value, 1 over the square root of 2k2, is nothing but that the velocity of the quark predicted by Griffith's law in quasi-static. So this slope, when epsilon goes to 0, is the same as in quasi-static. And this solution is valid until the film reaches the interface. Then, because of the change of the toughness, what happens? What is important here? Because of the change of the toughness from K2 to K1, there is a wave, a shock wave in this sense, which starts and goes to the boundary here. The speed, in this picture, the boundary of the velocity of the wave, because of the rescaling, is 1 over epsilon. So it tends to infinity when epsilon goes to 0. So it starts here, goes to the boundary, there is a reflection to the boundary, go force, and in the same time, the quark propagates with some velocity which I will give in the next slide. But this velocity is smaller than the velocity of the wave. And so the wave arrives here, intersects the propagation of the quark here, and when there is this reflection, this meeting here, the quark stops. The quark stops, and because it stops, it changes many things. In particular, the shock wave starts again back, and there is a lot of back and forth of shock waves, and the film does not move. So it's simply the solution of the dynamical problem. And after a certain number of back and forth of the waves, the quark starts again. With small oscillation here, with a slope which is quite similar to the slope corresponding to the result given by Griffith's quasi-static Griffith's law corresponding to K1. So, I will simply explain, so it's the same picture here. I simply explain this part of the picture here. So, when the quark arrives here, it changes the velocity. So, the velocities change, and the value of the velocity of the quark, which is given by Griffith's law, but in dynamics, so you have to take into account the kinetic energy here, and you find that the velocity of the quark now is this quantity, very strange quantity, with epsilon somewhere, but you can pass to the limit when epsilon goes to 0, and you see that the limit is this ratio between the difference of the two toughness over the sum of the two toughness. But remark that the velocity of the quark is of the order of 1 over epsilon. And 1 over epsilon is exactly the celerity of the waves. That means that the quark propagates not exactly at the celerity of the waves, but at the velocity which is smaller, because this quantity is smaller than 1, but of the same order. So when you pass to the limit, so that means that when you increase of the opening is more and more low, then you will see a jump, in fact, an instantaneous evolution of the quark. What is the value of the length here? But the value of the length is given by this formula, simply by solving the problem. And if you, so I have the value of the velocity of the quark during this phase, and so I replace here epsilon L dot here by this quantity. And if I pass to the limit when epsilon goes to 0, I find that. That is nothing but than the length predicted by the quasi-static conservation of energy. But it's the true result. It's not a triviality. Because, and why is it true? Because of the story of the kinetic energy in this situation. In fact, here is the graph of the energy, the kinetic energy in terms of time or in terms of capital. So, look at what happens. First, so the opening, so the speed of opening is small. The propagation of the quark is small. It follows approximately the evolution of Griffith's law in quasi-static. And during this phase, the kinetic energy is of the order of epsilon square. So it's very small. When there is a rapid propagation here during this phase, at the beginning there is continuity in time of the kinetic energy, of course. So when the shock wave starts on the left, the kinetic energy is rapidly increasing. It reaches a maximum when there is a reflection here. And the kinetic energy when there is a reflection is computed here. It's of the order of 1. That means it's not of order of epsilon square, it's finite. So the kinetic energy is finite at this moment. But when the shock waves start on the right, and when it reaches the front of the quark, then it becomes of the order of epsilon square. So it's small. And then the quark stops because conservation of energy, of the total energy in dynamics, but the kinetic energy at this moment will remain small forever, of the order of epsilon square. That you see that, in fact, kinetic energy in this problem, in this particular problem, is only important during the phase of rapid propagation of the quark. But it does not fix the length of the arrest. So the length of the arrest is given by simply by quasi-static consideration. So I have only to compute quasi-static, in this case, quasi-static energy just before, just after the jump, and I have to write that the energy is conserved in quasi-static without any energy, kinetic energy, only at equilibrium, and I find the good result. So it's the conclusion in this case. Important result. Important result. but it's not the rule in general. So, for instance, we have continued this type of analysis and consider not only one discontinuity of the toughness, but two discontinuity of the toughness. For instance, the toughness jump from K2 to K1, so decrease, and so from K1 to K2 increase. With the length where K1, where K is equal to K1 is a parameter, okay? And if this length is small enough, then you have the same type of solution in dynamics. So the solution is dynamics here. So you have back and forth of shock waves, a lot of back and forth of shock waves, the double of number of shock waves because you have two interfaces here. And you see that in this case, when the shock wave, the first shock wave, reaches the propagation of the quark, because this length is not large enough, there is kinetic energy in the film, and this kinetic energy does not disappear instantaneously. And that needs a large number of back and forth of waves to release the kinetic energy. So only when, so in this situation, I try to open the film here. I have a smooth propagation of the quark. When it reaches the first discontinuity, there is a rapid propagation until the interface, the next interface, this interface. But at this moment, the kinetic energy is important. It's not of the order of epsilon square. And then this kinetic energy will disappear only when the opening of the quark is large enough. So that needs sometimes to the relaxation of this kinetic energy. After some times, again, you recover the classical Griffith quasi-static solution. So in another example, or where dynamics and quasi-static are not equivalent. Okay? So my conclusion is, for this type of situation, it seems that dynamical consideration is very important in some cases, not on all cases, to find the good evolution of the quark with discontinuity in time. So, thank you. Question? One hour, yes. So a short presentation of fatigue, in fact. In fact, this talk is in the spirit of the work of Gianpietro. So I will reintroduce the concept of cohesive force model, or Barenblatt surface energy, and it is absolutely essential to obtain fatigue. And fatigue is nothing but, in fact, propagation of quark due to cyclic loading, or loading which is not monotone in time. So if you consider Griffith's law and cyclic loading, you cannot obtain propagation of quark. You cannot obtain fatigue. So you have to change the law of propagation. So the first idea is to take into account cohesive forces. But it's not sufficient. The other key point is to introduce an irreversibility condition. It is not trivial with cohesive force model. With Griffith, it's trivial. With cohesive force model, it's not trivial. And so you have to make choices for that. When you have made these choices, we can prove that, okay, with these ingredients, we can obtain propagation of quark with cyclic loading. And more, in fact, we can justify classical fatigue law like Paris law. I will explain what is Paris law and what is classical fatigue law. But this case is obtained only when the internal length that you have introduced here is small by comparison to the length of the body. So in 30 minutes, I tried to explain that. If you are interested by the details, in fact, all the construction in 2D is given in this paper with all the proofs, all the calculation. There is a lot of calculation for that. So in 2D, you have the proofs here. And the ID in one dimension for a simple case is given, for instance, either here or here in continuum mechanics and thermodynamics. So all the details are given here. So for people who do not know fatigue, I recall the problem. So if you have a structure like that, so it's a typical sample to identify some parameter of the material in fatigue or in monotone loading. The CT specimen here and beam here. And so if you prescribe to this body cyclic loading, for instance, you prescribe the displacement here, which oscillates in time like that. So the speed here is not very important. It's small speed, but it's not very important. What is important is the value of the minimum and the maximum of the loading, and the fact that the loading is cyclic. So you observe that in this specimen, L evolves even, so you see that here, Q evolves from 0 to the maximal value Qm, but Qm is the same cycle after cycle. And you observe in specimen like that L evolves with the number of cycles. Even you do not increase the value of the displacement Qm here. So it's typical of fatigue. Obviously, in material, it's classical material, that needs maybe 1,000, 1 million of cycles to observe a quark with a finite length. But we observe that, it's very important. If you try to model that with Griffith's law in quasi-static is the same as before. I recall that, it's almost the same notation. L is the length of the quark, G is the energy with weight, and GC is the toughness. So it's the same as K in the previous talk. So if you use this law, assuming that the behavior of the material is elastic in the body, except for the quark, you cannot obtain fatigue. In fact, in one cycle, nothing evolves. You can obtain an evolution of the quark during the first increase of the loading, when you release, when you decrease the loading, nothing evolves. But after the first cycle, so in the global situation, so if you compare the global quantity with the local quantity, so you prescribe the displacement, you measure the forces, and you draw the force in terms of the displacement. So you have an elastic response, maybe, and then a propagation of the quark when Q is sufficiently high with Griffiths. Then you decrease the displacement. So here is Qm. You decrease the displacement, nothing evolves. You have an elastic response. And when you prescribe the second cycle, in fact, you oscillate between these 2 points, and nothing evolves. So the behavior is purely elastic after 1 cycle, no fatigue with Griffiths. So you have to change that. So people know that from maybe 100 from a lot of years. And so they try to find phenomenological law to obtain good result in comparison with experimental result. In fact, if you make experiments, you find this type of law in fatigue. So here it's the rate of evolution of the length of the quark by cycle. So since the quark evolves after, so you break the sample after 1 million of cycle, you can consider that N is a continuous parameter, and you take the derivative of L respect to the number of cycles. N is a continuous quantity. So in this picture, you draw dL over dN in terms of delta K1. What is delta K1? You know that at the tip of the quark in elasticity, you have a singularity, and if you are in mode 1, that means that you prescribe displacement in such a manner that you have only an opening, a normal discontinuity of the displacement at the tip of the quark. You are in mode 1, and you have a singularity which is typically where at the tip of the quark, if R denotes the distance of at the tip of the quark and theta this angle, U behaves, the displacement behaves like K1, the square root of R, the distance here, and a function of theta. And U is a vector, F is a vector, and K is the stress intensity factor, which appears here. And so you have a singularity because if you compute the stress, you find that the stress is like that, with 1 over square root of R, with another function of theta here. And here you have a tension here. And so the stress goes to infinity at the tip of the quark. So you have a singularity, and the intensity of the singularity is given by this quantity K1. And so by experiment, you can measure for this type of sample, it's easy to compute K1 by using finite element method. And you measure the evolution of the quark at each cycle, and you find this type of law here with 3 regimes where there is no evolution of the quark, if K1, why delta K1? Because you could consider cycles which are not simple like that. So you could consider cycle like that with oscillation between 2 quantities, and what is important is the difference here. And so delta K is given by the stress intensity factor at the maximal of the loading minus the stress intensity factor at the minimum of the loading. And so we observe this type, no evolution of the quark if delta K is small enough, Then in log diagram, a straight line. That means that you have a power law in dl over dn in terms of delta k1. And then a rapid evolution of dl over dn. And when delta k1 reaches the toughness, k1c, in fact, you have propagation like with Griffith's law. That means that an instantaneous propagation of the quark. So, so this type of fatigue law are a consequence of observation here. And Paris proposed a power law, which corresponds to the second regime here, where you have three material constants, but one which corresponds to the toughness, the usual one, and two other ones which give the power m here, and here the value of the variation of the length of the quark, typically for certain material. So it's phenomenological. So what is the link between Griffiths and this type of law? And my purpose is to show that by considering not Griffith's law, but by introducing quasi-force model, you can make a link between Griffiths and Paris. In fact, Griffiths is in some sense a limit of Paris law. So I claim that by using quasi-force model and the good irreversibility condition that I will explain later, we can prove that the evolution of the law during cyclic load is like Paris law. So, quasi-force model, Gianpietro explains that this morning. Maybe it's not the same notation, and there is a mistake in my picture, because in Ecole Polytechnique, so Ecole Polytechnique is the better school in France, and because of that, the notation are not the same. The notation are not the same in Ecole Polytechnique. The displacement in Ecole Polytechnique is xi. And u, for you, is u, for me also. So, but in Ecole Polytechnique, the displacement is xi. And so I use xi in this picture, but it's not, so in u in other one. So you replace xi by u. And so I will use quasi-force model of this type. I think that Gianpietro, you use for this function maybe theta. I call that phi. Yeah. So gamma is the quark. Okay. Un is the normal displacement. I only consider normal displacement. That means mod 1 opening of the quark. And the brackets are the jump of the normal displacement here. So quasi-zone model consists by saying that the density of surface energy is not like in Griffiths 0 or GC, but a function of the jump of the displacement, with a function which is most increasing. Concave is better, because with concavity you have a decreasing of the quasi forces with the opening, and so continues starting from 0 with a slope which is sigma c at the origin, and we reach GC at infinity at a finite value of the jump. You obtain from this function the quasi model, in fact the force, which is a normal force in our case, where there is only normal jump of the normal of the jump of normal displacement, sorry. And so the forces are only normal, and you compute the forces by the derivative of phi respect to the jump of u. And if you choose this type of function, so sigma n is decreasing on sigma c, the slope here, to 0. So it's classical quasi-force model, but so the same. The problem is that we cannot use exactly this type of formulation because you see that there is a problem if you consider non-monotonic loading. In fact, you have to precise how the cohesive force evolves when I am in the situation of loading or in the situation of unloading. And so I precise that here. So the key point is to say, in fact, the surface energy density is no more a function of the value of the jump of the displacement at time t only, but depends on all the history of the jump of the displacement up to time t. So the history is important. For that, one possibility is to say, in fact, phi depends not only of the jump at time t, but some quantity which is the memory of all this history. You can make many choices. And so you have to, if you make a choice, you have to see if this choice could give you a good result. I will try to explain the result after. One particular choice in mode 1 case is to introduce the so-called accumulated opening. What is this? In fact, delta dot, so dot is the derivative with respect to time, is not u dot, the jump of u dot n, but the positive part of the jump of u dot n. That means delta dot is increasing only when u dot is increasing. When the jump of u dot n is decreasing, delta dot is equal to 0. If I make this choice, look at what happens. So consider a simple case where at the point of the crack here, I have an evolution of the opening. Opening is the opening is the jump of the normal component of the displacement. So assume that at this point the opening evolves like that. It's with cycle from 0 to some maximal value here. If I use my definition of the accumulated opening, the evolution of delta in terms of t is the following. During the increase of opening, delta evolves because delta dot equals the jump of u dot n. But during the phase of decreasing of the opening, delta remains constant. And cycle after cycle, with that, delta becomes larger and larger, while the opening oscillates between 0 and the maximal value of the opening. So if you consider that the surface energy density is no more a function of the opening, but of the cumulated opening, what happens? I consider here Dugdale surface energy density. Dugdale surface energy density is the surface energy density with a straight line here and the constant here. And the slope here is sigma c. Okay? Very simple model. So with this model, in the case of cyclic loading, delta is increasing cycle after cycle. So after 3 cycles, delta becomes larger than delta C. So the surface energy density becomes equal to Gc. And since the cohesive forces will be, in some sense, the derivative of this function, it's explained below, there is no more cohesive forces after 3 cycles. While if I use only the opening and not the cumulated opening, if the opening here, the maximal opening, is small enough, there is oscillation of the opening, and simply there is always cohesive force. So no fatigue if I don't introduce this type of history. So if I introduce that, and phi becomes a function of the accumulated opening. To compute, to obtain the cohesive force, it's a little more difficult. In fact, all what I try to explain can be obtained by variational arguments, but it's too more difficult to explain in few minutes. So you can read all the details here. I explain the result. So the cohesive force will depend both on delta and on the rate of opening, so the jump of u dot n. Not only on delta, also on the rate of opening. If delta is greater than delta C, so you have reached the critical value of the surface energy density, and there is no more cohesive force forever. So sigma n will be equal to 0 if delta is equal to delta C. If delta is between 0 and delta C, then you have to consider either if you are in a case of increase of the rate of the opening, in the case of the decrease of the opening, or in the case where the rate of the opening is equal to 0. In the first case, when the opening is increasing, you say that you take the derivative here, and so sigma n is equal to sigma c, this slope here. In the case where the opening is decreasing, you are in the situation of passive cohesive forces, and you say that the cohesive force is equal to 0. And when u dot, the jump of u dot n is equal to 0, in fact, sigma n is between 0 and sigma c, and not exact. It can be, the interval is 0 sigma c. And I will use that. So you see that you have to know at each time if the cumulated opening is in the interval 0 delta c or greater than delta c, and to see if the opening is increasing or decreasing to obtain the value of the cohesive force. And I claim that with that, we can obtain fatigue law like Paris law. But it's not easy. We have a lot of computation, of proof to check and so on. I explain the great lines. For instance, so a typical example, CT or a problem where you have like CT sample, and you prescribe displacements which are oscillating in time like that. So the notation are not the same, but so it's UM, the maximal value, and you make cycles like that, and on one time, the typical situation is this. First of all, I assume that I know the path of the quark. That means that I prescribe this type of law for cohesive zone only on a prescribed surface. So assume that I know the path of the quark. Typical situation is the following. When at a distance problem I